Testing 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Hello, test. Okay, breathe. Testing 1, 2, 3, 4, 5. Testing 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Hello, testing 1, 2, 3, 1, 2, 3, 3, 2, 1. Testing. Hello, test. Yo! Okay, just a second.
the Wyoming folks?
Well, they've been kind of close by. They're with that, consulting with them. So this is the lecture wire.
Oh.
So I'm going to be looking at it from this side where the meter is. Z meter stick. So we're going to be measuring.
No. That meter looks familiar.
Well, it's one of many. That's one
Yes.
I've had for ages. So
Uh-huh.
we're going to be measuring wavelengths.
Okay. And?
Well, that's want to be able to see what I'm doing here. So we can.
And then what are you doing with this?
Well, I'll show you. That's my shorting stick. So.
Oh, okay. I hear somebody pulling up.
Yes.
So did you ever send back that big gold keyboard that
Oh,
you
I did.
fixed?
Yep, I did.
How much does that cost to ship to
Just
wherever?
about $100.
And it was going to where? How far away?
Anchorage.
Oh, just to Anchorage.
Yeah.
So they just, you paid that, they reimbursed
Yeah,
you?
yeah.
Yep. So the little part that you ordered from Japan worked just right, huh?
Well, that's actually from their main store in Seattle.
Oh, is it Seattle?
Yeah.
Oh, okay. So is this up and running yet?
Yes, it is. Well, it will be. Oh, that's it. Yes. See, it's right there.
What's this brown stuff?
It's cork.
Oh, that's cork.
Hello, hello.
All right, here.
You are here.
Man.
Ah.
Oh,
Hi.
hi. Oh, this is gonna be fun.
Yes, it will.
Oh, wow.
Hello, good to see you again.
Good, yeah. Wow. With a minute to spare to grab some coffee.
Sure.
Or we start. Would you, want to grab me a bottle of water, please? Oh, yeah.
There's some right here.
Oh, perfect.
Yes, right here.
I fixed up, I have a metal water bottle I carry with me everywhere.
Ah.
My wife grabbed it and washed it. I said, well, I'm taking that tonight. Yeah. And it just whoop, totally threw my groove off, you know? Same here.
I'm an official camera person here again.
It's like a xylophone.
Yes, that does look like it, yes. Yes, where are the hammers?
Yes.
Whoops. Stepping on your stuff here.
Yeah.
What is, let me see.
That is a microwave test set. It has both a Plystron transmitter and a detector.
I knew that.
You do it.
No.
Eric, did you want to move the empty box there out of the way so people
Oh,
don't trip over it? Doing just that so people don't trip.
Oh, look at the wave guides in there.
Yeah.
Wow. That's a test, just a test set.
Yep.
Huh.
7 gigahertz. 7 gigahertz.
Very cool. Did you get that this last year when you?
No, I forgot it with one of the silent key sales in town. Silent key, pick it up, or else sales.
Yeah. Very neat.
Rather elaborate socks.
Yeah, the ones that you and Priscilla gave me.
Ah, there.
They're loose and everything on it. Yeah. Fusatron fuses. Slow blowing.
Slow blowing, yes. Fast blowing.
I started taking the practice tests for the extra class. I'm probably going to be ready for that in a couple of weeks.
Oh, good. So I don't know who's doing the DEC now. Probably Jerry Curry is kind of in charge of that. So
Jerry is?
I think so. Yeah.
KL7AJ GROL?
Yeah.
Okay. I'll get with him and find out when the next
Yeah.
class is. I was shocked at how much stuff in that test we've been covering.
No, that's good.
I mean, there was quite a few things that, I mean, some of them, there was down to like 2 answers, and I was like, I know we talked about this. And one of them was the open and the short
Oh, yeah.
on the end of a feed line. Like, we just went over that.
Yeah.
And I got it wrong. Well, it was a trick question. Well,
Harris.
it was an eighth wave.
An eighth wave.
An
There we
eighth
go.
wave instead of a quarter wave.
That'll
So I clicked, I checked infinity as the answer, which is wrong. Because it's an eighth wave, not a quarter wave.
So it's half of infinity?
There you go. And then divide by 0.
So the question is, what is infinity over infinity?
Yeah.
Einstein made the mistake once. He divided 0 by 0 and called it 1, which for everything else works, but that's one of the exceptions. Yeah.
But infinity over infinity could be 1?
That's also undefined. But,
Yeah.
but I like those T-shirts, as they say, I divide by 0.
Are we waiting for one more?
One more.
James gonna show up? Okay, good.
No, haven't heard. It's not coming, so
Wow. What are we doing today? What are we launching?
we are doing the electric wire,
Okay.
electric line, the oldest instrument in all of
You said this was invented in, what, 130 years ago or something?
Well, actually, it's 1880s.
And you're feeding it with a box. I gotta go.
A box. Yes, I'm feeding it with a box.
There's a box connected to it.
See what that is.
It's secret.
It's a secret.
It's all sealed up.
Oh, okay.
Can't see in it.
Black box. Huh.
Pretty silver one. I'm guessing it's a frequency generator.
I want to see if I should motorize elevator on your thing.
Yeah. Well, we're going to be taking readings. And probably we could move this around and get a different reading. Maybe.
Is that an amp?
Microamperes.
Microamps. Amperes.
Huh. Oh, well, if we move it around, it shouldn't. Pretty light? Yeah.
Not gonna shake it though. It won't go that far. I got my new manager that I hired a couple months ago.
Yeah.
She's very interested in ham radio.
Oh, good.
Really?
She's been watching me, and I've been getting a lot of QSL cards lately. I sent out a stack of about 20, 25 on Tuesday,
Oh, okay.
and I've been actually getting a lot of folks sending out cards, which I find really neat.
That is neat to get a
It's
card.
very old fashioned still, but
Right.
especially everybody wants to do EQSL,
Sure.
e-cards or no card.
Right. But they're responding, huh? Very cool.
I don't like the FT8 ones because I feel like I'm cheating.
You are cheating.
It is. I haven't printed out a single award I got on FT8. I won't even recognize it until I get it on phone.
Well, I occasionally let mine run and let it put spots out there so
Yeah.
people can see. There's a lot of different things.
Somebody's driving.
Yes. Yeah.
You're right. Vehicle.
Mark, it's feeling cooler down here than usual.
Well, I turned
Is
the
it?
floor on earlier. That's floor is still heating up.
Always a little cool in here.
You do our jumping jacks or do that.
Yeah.
We have a whiteboard.
Japanese auto assembly line where they do the calisthenics there.
Yeah.
Towel in the
Yes,
back.
you should start your class with some exercise to get the heat flowing.
We have a whiteboard downstairs. And I try to write little things on it. Sometimes they're, enlightening or funny.
Yes.
Today I wrote, before the crowbar was invented, crows drank at home.
Yeah.
In my class with my electronics instructors in college, they say, well, I taught them everything I know, they're still stupid.
Yeah.
So does that reflect on that? Yes.
I've cut this board 3 times and it's still too short.
Thought I heard a car coming up.
Yeah.
So I wonder if they
Give them a little.
turn around to park in front of our garage and are walking down, maybe.
I park on top.
Oh,
Right on
okay,
out there.
he's probably talking to someone.
Oh, it's 6 o'clock.
It is 6 o'clock, yes.
Sniper net's on.
Sniper nets.
Nice.
Nice signal.
Yeah, nice quiet location here. So.
All the way from Anchorage? Nice. Hey. How's it going?
It's going well.
Good.
I like the sweater.
Thank you. Alpaca.
Yeah.
Yeah.
I have socks
Something
with
legit.
Alaska critters on.
Oh, nice.
Not as fancy, not alpaca. I wish it were
I bet
alpaca,
that's
that's warmer.
Oh, yeah. That's
Wow.
super nice. Oh, yeah.
Oh, very nice. Very nice.
The only thing is the dog hair likes to stick to it.
Oh, yeah.
We have a cat that has selective shedding.
Oh, yeah.
If I wear something black, he sheds white fur, and if I wear
Oh, yeah.
There you go.
That's funny.
Yeah, very nice.
Well, I guess we can kind of get started here.
Yeah.
So,
The important people are here.
yeah.
Hey.
So, any questions on last week? Did you enjoy the shy wave machine?
Yeah.
Okay, well, we're going to do the electronic equivalent of that today.
That's what this is. I was very impressed with that video.
Okay, well, I'll press you more, so I guess you
Ha.
So this is called a Letcher line, the oldest instrument in all of radio, and
Electro.
Letcher, named by Ernst Letcher. He was a German engineer. He was a contemporary of Hertz, and so this it demonstrates transmission line phenomenon, just like the shy wave machine, except it's all electronic.
Oh, yes.
So what we have here is 2 parallel lines here, and unlike the rotating rods here, this is actually a transmission line, and we feed it with an oscillator at that end, and it's open at this end, and then we have a detector that tells us what the voltage is at any point along here. So if we come on this side here, you can fire this up, and Joe will step around me as we take pictures. Oh, so we turn this on. We have an oscillator, and we have a meter there. And what we do is we slide this meter along the way, along this line here. We see we have peaks, and we have valleys, and we have peaks, and we have valleys, and we have peaks.
Yeah. No kidding.
And actually, I need to bend this down a little bit so we make a little better contact. There we go. I have to retune it. Actually, I think I like it a little better with that. Not quite in contact though. Capacity.
Oh, yeah. Wow. That's the spot right there.
Yeah. So
Wow.
the nulls are actually much sharper than the peaks. So if you want to find out what the wavelength is,
Go to a null,
go to a null, and then the next one, that's going to be half a wavelength.
right there.
Really?
Right, so there's half wavelength there. And if we measure it here accurately, what we can do is find the difference between nulls there. So, and with knowing that, I'm going to let one of you guys, or all of you, tell me what the frequency of this is.
Well,
Is that a yardstick or a
That
meter
is a meter stick.
Okay.
So you can pick any reference here as long as it's
okay.
in there.
How far? We're at,
So you could say 40, because that's on that back leg.
On the back leg.
I'd say 40 is a good null.
yeah.
Okay.
And 58.
8? Yeah.
57.
57?
57.5.
Okay.
Okay.
So what? 57?
So 40 to 57.
And those are centimeters.
About 5 megahertz, roughly.
17 times.
So we'll go to the magic drawing board.
Whoops, watch yourself there. There we go.
I just got 5.
Yeah.
But
So it's about 17
So,
centimeters times
17
4
centimeters,
times, yeah.
which would be half.
little c,
That's a half wavelength.
little c is what? What's the speed of light?
300
Okay.
million meters per second.
Per second.
Mm-hmm.
Oh, the camera went down.
That's what happened.
Oh.
What is going on here?
There we go. Okay.
Is it going to stay?
Okay, 300 million meters per second, okay? And what we want to do is find out what fraction of that is. So we moved how many centimeters?
17.
17 or
Centimeters.
quarter wavelength. You want the full wavelength or you want the
Half wavelength.
half? Oh, okay.
Well, we want to ultimately find out what the full wavelength is.
I could just
But
multiply.
we moved, the distance we moved is half a wavelength.
Oh, we did move half a
We
wavelength.
moved half a wavelength.
Oh, I thought you said quarter. I thought you said it
No,
was
we
a quarter.
moved half a wavelength.
So 34 centimeters is full wavelength.
34. Yeah.
Is, lambda, okay?
Okay.
And so frequency is c over lambda, right?
Yeah.
Okay, so 34 centimeters is how many meters?
0.34.
34.
Okay. Okay, so what we have is 300 over, or we could use 300 million over 0.34 meters, 300 million meters per second. So what do we have? 300 million over 0.34, what's that?
That 800.
882 million?
Okay, 82 megahertz.
Megahertz. 882 megahertz, huh? Oh, so it's very short.
Okay. How accurate do you think you are?
I'm going to bet it's extremely accurate.
Well, let's turn on
pretty high.
spectrum analyzer and find out.
I'm going to bet that's pretty dang close.
That's pretty high, isn't it?
882 megahertz?
Make it like
No.
point, whatever that is,
Oh,
and we'll really get accurate. 0.352.
That's pretty low frequency.
82.352.
Yeah.
just don't stand right here.
You got for me?
So what do you got going on over there?
There's a spectrum analyzer, so
He's
with
reading it.
Antenna on it?
the antenna on here, so we should be able to receive that pretty nicely here.
Oh, yeah?
There's the FM broadcast band here. There's
Oh, so you're used to dealing with like 5G.
Yeah. Gigahertz.
What are you,
Yeah.
right. What do you broadcast?
Huh?
What do you broadcast?
10 megahertz would be like 30 meter.
Okay.
What are the limitations?
14.
Yeah.
What's that? They've got a new radio out that'll do 10 gigahertz.
Really?
Oh, okay. That's the one I was talking about, the transmitter is actually at the antenna, and it's connected with the Cat5 wire.
You said gigahertz, right? You said gigahertz?
Gigahertz. Wow. Yeah, 10 gigahertz is the highest I've seen.
That's
Way within the amateur.
Wow.
Got 868. Right there. And 89.
89. Nice. What did you say it was?
82.
Pretty doggone close.
What do we got? Whoa. Wow, what a spike.
Very good. Very good. Now, before you have frequency counters and spectrum analyzers, that's the only instrument available.
Really?
So this was the state-of-the-art frequency counter before.
Wow. And you only needed half a wavelength
Yeah.
for the okay.
And you had to know how fast the speed of light was.
Yeah.
Right.
Now this, since the spacing is so wide, the velocity factor in this is probably 99% of the speed of light. Coax cable I showed is about
Right.
60%.
60%.
60 to 70%. So anyway, very good, very good.
How does the spacing increase the?
The closer it is, the slower the velocity factor.
It is.
Yeah, later.
Because
Yeah.
it's acting like a.
Uh,
Why is that?
Well, it's because you got
Space between the.
more capacitors between it, which acts like a delay line.
Oh yeah.
And so we'll do we'll do everything he did with his demonstration with the.
So we're going to short out the end. And
We're going to short out the end.
Very nice.
Okay, so now if we move this to where we have a peak, we can do that up here. There's a peak. And what we can do is we can put a short here. We do the same thing here. So where we had a peak before, we now have a short.
Wow.
And then as we move this, the distance between there is still. So the distance as I move this is still going to be the same.
that's going to be 17 centimeters.
Yeah. Same thing here. There's a no
Now the short
and a no.
we're creating acts like what in his demonstration?
This is when you put the clamp on the end,
Yes.
it did allow it to rotate.
Yeah.
And with an open here, it's with an open. So
With an
the
open,
reflection,
okay.
with the reflection is going to be in phase with it open, and out of phase it's going to be closed.
When
Or
it's
upside
short,
down, yeah.
When it's short. Or okay.
Upside down. So now, remember
Completely
what he
out of
did.
phase, 180 out of phase. Like
Yeah.
out of, okay,
Yeah.
wow.
So remember what he did to prevent, so you didn't have any standing waves?
On the demonstration?
Yeah.
So he didn't have any
Yeah.
standing waves?
What did he do? So
He put it in a thing of water.
He,
Yeah,
he
put a
blocked
dash
one
line.
side.
okay, so
Or
put a
he-
dash pot on there, which is match the impedance of the transmission line. Okay, so what I have here is a resistor, which is about 680 ohm, which is about the
Oh yes.
He put that glass of water with the.
Yeah,
that
dash
little
wire.
wire dangling.
So now if I put this here,
Uh-huh.
we'll see we should have very little change in the voltage as we move across. There will be a slight theory, but see, it's pretty decent.
Yeah.
Because it's matched, so now we have all the energy is absorbed in the resistor, so we don't have any standing waves coming back.
Nothing's
Oh.
returning.
Yeah, nothing's returning.
So you're turning it into heat.
Yeah.
Maybe there's not the same amplification of the.
Yeah,
Is that why?
yeah, we're just looking at the voltage we're putting out, it's going to be absolutely constant across here. That's why it's called a flat line.
Wow. Okay. Class dismissed. Just kidding. That's awesome.
The fundamental forces
So that-
of
Can you
nature.
feel heat?
Oh, no, no.
It's
It's
the
just a
fact
few
that you can
microwatts.
physically do that
Mm.
and then electrically do the exact same
Yeah.
thing just blows me away.
Yeah.
That is so
Yes.
amazing.
All waves act alike.
Yeah, yep. So we could do the same thing with a standing wave ratio if we wanted to. We can measure the difference between peak and valley. However, this is not a calibrated scale. It's just a relative scale.
Sure.
But if this were a calibrated scale where I could read actual voltage here, what I could do is measure the peak difference between the peak and the maximum and minimum, and it'll tell us what our standing wave ratio is.
Because there's an equation for that.
There is an equation for that.
I don't have that
It's
memorized.
SWR
I
minus,
remember you doing it.
SWR minus 1 squared over SWR plus 1 squared.
Yep.
And that's, yeah. So we've already,
What was that called again? The standing wave?
that's the standing wave ratio. It's actually the equation tells you that actually reflected power as a function of standing wave ratio.
Oh, wow.
In the radio world, you really don't want power coming back into your radio. You want it going out and not coming back.
So you're using resistors and things like that?
You know, you don't want to use resistors. You want to use radiation resistance of your
Oh,
antenna.
radiation resistance, yeah.
A perfectly tuned antenna will use all of the
Yeah,
energy. None will come back.
okay.
And if it's
Right.
not perfectly tuned, then you can use air gap capacitors to
change the...
and an inductor to match it.
Now, in the demonstration, he set short pulses down a transmission line.
Yes.
The way I do that is not with this, but I go over here with a pulse generator,
Whoa!
and that will demonstrate something with
That's square pulse.
square pulse, or very short pulse.
Okay. And why square pulse, not, just...
It could be any pulse, but have it very short.
Yes.
So what I have here is, here's an outgoing pulse here,
Okay.
and that's repeated about every, about 100 hertz, so.
Am I supposed to try to put the camera over there?
If you want to walk on here and do that, you're welcome.
Okay. I'll give it a try.
Repeated.
It's kind of an arbitrary frequency as far as the repetition rate here.
I got it.
I got it.
Just want to make sure I don't trip over any chairs.
Then you got a big box here, we'll have multiple cameras. Get my,
Thank you.
get my monetization.
Yeah.
Okay.
So what we have here is a short pulse being generated by your pulse generator here,
Okay.
and it's about a 0.1% duty cycle. So very short pulse in terms of its relative amount of time. I'll come around here, take a peek here, take out our pulse. Okay. Now, if I put a unknown transmission line on here, what we have is a second pulse, which is reflecting from the far end and back.
Ah,
Now, we can tell how long that distance is by measuring the time between here and there. Now, since it's a round trip, we know this time is the transmission line is actually going to be half that distance here. But what I can do is I can put my cursors on here, and what I can do is put one cursor at the beginning of my outgoing pulse here, and then I can put a cursor on the reflective pulse here. And this will tell me the difference between them. So it's 136 nanoseconds.
okay.
So,
You want to divide that by 2? Is that what you said?
well, actually, it's 136 nanoseconds. Yeah, that divided by 2.
There and back.
Yeah. So that's that. So we take that. So it'd be about 100. That'd be about 83 nanoseconds.
Okay.
And then 100 would be about. I'm sorry, it'd be about 63 nanoseconds. Now, to a very, very loose approximation, light travels about 1 foot per nanosecond. A nanosecond is a billionth of a second. So one foot per nanosecond.
Okay. That's
Now, the
easy.
velocity factor of this is somewhat less than that. It's probably about 60% of that.
That's 60, okay.
So now what we can do is we can take that, and if we go to well, using the 136 nanoseconds and take half of that,
Okay.
that'll be the approximate length, and then we multiply that by 0.66.
Okay.
Good approximation.
Goes time 0.66, right?
Okay, and what do you come up with?
4.8
Okay,
or 4.9?
okay, about 50 feet.
Yeah. Wow.
Now, this technique is used for finding broken cables underneath the ground where you don't have any way of getting to them.
Wow.
So it's called TDM, time domain reflectometry.
Wow.
Find the length of any
that work on any wire, or does it have to be a coax or a transmission line?
Transmission line.
It has to be a transmission line to work.
Yeah.
You can't just put it on a wire and expect a
Well, a wire actually does have, if it's in proximity to the ground, does have some,
gotcha.
You'd have to know what that
Yeah.
speed multiple was, though. Like coax, you know, it's point
you
six.
know, yeah.
And other lines are close to the speed of light.
Right.
Well, you could calibrate that if you took a
Well,
note.
good.
Yeah, you could.
Now,
With
it's
that,
reflected, it's an open line, so we know it's going to be reflected in phase, right? So if we put a short on here, the reflected signal is going to be upside down.
Oh, look at that.
Come on now.
Okay. That's
Wow.
reflected in phase and out of phase.
Out of phase.
Wow.
And we don't want any reflection.
Resistor.
The resistor is equal to what?
Each are two.
The characteristic of P's of Y. So this is 50 ohm coax,
Okay.
and 50 ohm terminator. And pop that in there.
Wow.
No reflection.
No reflection.
Why would that the character?
but it's still mixture.
The characteristic
Yeah.
of
Yeah.
a transmission line?
Right.
For that coax it's 50 ohms.
Yeah.
For others, it's 75. For
75.
open wire, it's 450.
Why do you want it to match?
Well, because we want all the energy to be absorbed in the load, which is what you're actually trying to accomplish.
Right?
So anything that's reflected is energy taken away from the load. So if we have a pulse here, in this case it's 100% reflection, so we aren't,
Right.
aren't getting any power transfer to anything.
Right.
That's like what we use at my job for testing. We have a dummy load like that,
Mhm.
but then there's actually a test port off the end of it. So you're not getting any reflection back to your device, but you can see what is hitting the end of the wire.
Now I can get a partial, terminators here.
Partial reflection?
Partial reflection.
That was easy, man. 50 ohm, 50 ohm.
50 over 50.
Yeah.
Finally, something I can remember. Yeah. Does it make sense to you why they should match? Why the impedance of the wire should match the resistor?
Okay, and some other terminators here. Let's see,
The line.
75
If it's, you end up getting lost. If it's a signal, you're going to lose some of that signal on the way to the antenna.
Okay, so here's a,
Lossy.
here's a 75 ohm termination. What do you think the
Okay.
reflection will look like?
All right, so 75 ohm on a 50 ohm. It's not short. It's going to be closer to a short than a 50 ohm resistor. So I'm thinking you might get a slight out of phase reflection. Not quite out of phase, but definitely much smaller.
Yeah, the time, the distance is going to be the same, but it's not quite matched. But if the impedance is higher than the line, of 75, it's going to, the little wave's going to be up. If it's lower than the line, it's going to be a pulse.
Oh, that went backwards.
Yeah.
Okay.
So I don't know if I have a 30 ohm terminator down here.
I went the wrong way.
Oh, that's a 50 as well. Others are all 75, so, you know, almost all your transmission lines in common use are either going to be 50 ohms or they're going to be 75. No, I do.
What's that one?
It's going to be something, probably.
Oh, because the lower ohm resistor allows like.
Well, lower, it's going to be closer to like a short, so it's going to be below the line because it's going to be flattened out, primarily out of phase. And let's see, so I just add. So, any questions?
He was asking about the why you wanted to match, and I was like, from a radio perspective, I answered, but he might want to ask you that question.
Well, let's say, when you're using weak signals, if you want to look at the waveform of a signal, you want to know what it really looks like. If we have reflection, that's going to screw things up. So if as a matter of fact, if I can, let me freeze the repetition rate here quite a bit. Okay, here's your prime example. So here we have our reflected wave superimposed on our outgoing wave, so that's gonna speed things up. Now, especially with stuff like radar, or where you're trying to find exactly how close it's going to that, or even in video, if you have overlapping signals like that, you're gonna get ghosting built into it. It's just, in television, it's very critical that we have a perfect match, because otherwise you end up with building a ghost in the system at multiple transmission of the same side, so that is a superimposed outgoing and incoming pulse.
And it's double the height.
Double height, because
Because
they're coming back as adding, yeah.
It's adding to the
There's a
existing peak.
principle we call, the most
Yep,
important
yep.
principle is called superposition.
Yep.
Where every time you, on any medium single wave, you have, you can only be at one voltage at one time. So if you have two voltages superimposed on there, they have to,
Doubles the
they have to
voltage.
have. Or if you're out of phase, they have to.
Is that what they call being in compression?
Well, not really. Compression is a non-linear. This is all linear, which means it all follows Ohm's law strictly. There's no non-linear devices in here. We'll get into non-linear devices later, diodes and all sorts of stuff like that.
Because we, in my line of work, we deal with compression fairly often. If we have things not set up correctly, it
Yeah.
looks similar to that.
Yeah.
Of course, that's on a, what do you call those? Spectrum.
So we'll go into non-linear devices like diodes.
Okay, yeah, that's a different thing.
But this is all linear. It's just pure addition and subtraction and timing. So, everything behaves the same. It's like mechanical resonances. So we were talking about waveguides a couple last time, and I just said I can show you.
Back over there.
You got those in the truck, right?
Oh, yeah. Built into the dash. Wow.
Microwave.
Microwave test set is designed for around 7 gigahertz.
Professor, do you want me to go around the other side of the
Yeah, you
table?
can, sure. Depending on how it's fascinating to you.
Microwaves around.
Well, microwave starts
There's gotta be an
basically
easier
officially starts about 3
I remember when this was all empty in here.
That was a while ago.
Three up to
Well,
one.
ultraviolet is
Like nothing in here when I first saw it.
Can you believe all this?
microwave is into
Yes,
light
because I actually used my trailer to help me move, so I do remember all of this.
Okay.
Oh, gee.
Bless you.
Bam. Okay.
terahertz. Okay, so we talked about waveguides a little bit here before, and this has lots of waveguides in here. This red device here is a reflex klystron. That is actually an oscillator that oscillates at 7 gigahertz. So you see here, it actually has a mechanical compression, which changes the actual dimensions of the cavity, the physical dimensions of the cavity. And that's your coarse tuning. And then there's a repeller voltage, which is this, says right here, says reflector, which changes the voltage on the anode of that. So it's basically a vacuum tube. But it got some
Adjustable.
yeah, this is adjustable where you can change it. So this lip generates a signal, pretty weak signal. It's a few milliwatts, but it's just enough for testing. So you adjust the coarse frequency here, just the output frequency. This is your transition between microwave or between waveguide and coax.
Oh.
So it's waveguide underneath and coax up on top here.
Wave guide.
Yeah.
This is wave guide.
That's
Now,
waveguide.
the coax.
Yep.
Okay, I wonder what that transition looks like.
So that I have one, a raw one here.
Does this thing still work?
Yeah, it's shooting out that way, so I wouldn't stand right there. No, I'm just kidding.
asking.
Does this thing still work?
Oh, yeah, it's very clean, so you don't have anything to calibrate it with. But so this is a waveguide coax transition. You see there's just coming in from the center conductor of coax, it just goes through that insulator.
Right.
So it's a little spike, this little probe.
Yeah.
And that's the capacitive probe there. So
Really?
I mentioned that the main mode of propagation in the waveguide is a transverse electric field, a TE1 mode, which is the on the narrow dimension this way, we get the electric field going that way. So if we just have it just like an open wire feed line, you have a maximum voltage crossing. So then what that's doing is just sampling the electric part of the field there.
Really?
And your satellite dish, probably a couple of satellite feeds.
I was dealing with one of those earlier today.
There you go. Have you ever
No wonder you don't
torn
wanna
one
see
down and see like how it connects and all
Oh,
that?
no, I don't get that
Like, is
It doesn't work.
it right?
Exactly. Those are you know.
Does it?
I'm a tech, not an engineer.
This one doesn't work. Give me a new one.
No, they are fascinating though.
Cool.
And actually, I've never had one of those not work, to be honest with you.
Probably pretty simple.
Yeah.
Since there's no moving part.
Mhm.
That,
Now here's a satellite feed, and there's the probe inside there, but that can rotate around so you can change the polarization. So since this is round here, it's non-polarized by itself. So the only polarization you have is the rotation of that. And then it comes out of here, and then it's right to the that here.
When you say satellite feed, this would
This
be
feed on the dish.
the
This is feed
On the
dish,
ortho
correct, dish.
to receive.
Yeah, or transmit, you know.
Or
This would not be for transmit. But,
Oh,
That's what faces the reflector.
And so it can sense if it's polarized, it needs to move so it
Yeah.
can receive.
Yeah.
Gotcha.
So as a satellite's rotating around, we're in space here, and the polarization.
Oh, sure.
Slightly, they try to keep it stationary, you know,
But still, the
but
satellite.
you have on any satellite, you have the capability of doubling your channel capacity. You can use horizontal or vertical. So as long as they're at right angles, it could be, you can have zero interference between them.
That's what I was mentioning with our stuff, is why we have to focus on that when you were explaining the 90-degree
Yeah.
phase shift, is because they do that off
Yeah,
the
they
bird
do.
that we're bouncing off of, and they sell it to two different people. So if we're off phase, we're actually interfering with somebody else that's renting the other
Really?
polarity.
So, yeah, you can theoretically get infinite attenuation between them. It's pretty
Yeah.
close. It's usually like 80 dB, but it's more
Right.
pretty close to it.
Infinite, wow.
So let's see here. Okay, now the power measuring. Remember I mentioned the tune cavity for measuring frequency? So that's this thing here. What it is, there's a cavity with a piston in there, so it changes the dimensions of the cavity. And when the cavity's at the resonance frequency of the signal, it's passed on through. And then what it does, it comes through here, and it heats a little device called a bolometer, which is a temperature sensor. And this is a little thermometer on here. So you turn this till you get the maximum temperature on there, and you say you've got your tune at that frequency. Now there's a calibration chart for this. I don't have it, but for just a standard
It looks like a
micrometer.
micrometer here.
It's a micrometer. So there's a
Really?
calibration of frequency versus the actual
Gotcha.
position.
Question. What's in this right here? Is that like a ferrite rod or what is that in there?
No,
What is that
the
in?
bolometer is there's several metals you can do it. Most semiconductors will do it. You can do just a pellet of semiconductor material. A lot of metal oxides will do it. That as they heat up, even wire. So as the microwave is absorbed in that little pellet,
Uh-huh.
it converts into heat, and then we're just simply measuring the temperature.
And this,
What
that's
that-
this, what about this?
Yeah, what that does, that adjusts this whole point here is to find the frequency.
Oh, yes,
So you adjust this till you get the maximum heating, which means you're getting the maximum
right.
energy
And
through this tune cavity.
I was just asking, what is a tune cavity? What is in it?
Tune cavity is a piston. It's a round cylinder with a piston on top and two coax probes on the inside.
Oh,
And I can
Ah.
draw a picture of them.
and so when they're the proper distance apart,
We got a tank here, we got a cavity here, and we got a little passive probe just like you have in there, on both sides here.
on the sides, okay.
On the side. And when this is tuned to resonance, you'll have the most transfer energy there. So you change the volume of that cavity in there. And it's calibrated with that micrometer, and then
Wow.
there's a partial conversion chart here. That, now, a lot of your VHF rigs now use what's called a helical resonator, which is a partial, it's a sort of cavity. But if you worked at any repeater sites, you have these big tanks there. There's the knob on top, and that's your tube cavities for rejecting, so you can reject a receiver and pass a receiver. Reject transmit frequency in your receiver, so you use the same antenna for both transmitting and receiving.
There was one of those in the room I was working in today at the police station.
Yeah. So probably a six packer there. So
No, there's only four.
only four. Okay.
Four cans, and I was,
They can get very elaborate. I've been in Mount Sutro in San Francisco there, which has 12 TV stations on one antenna.
wow.
Yeah, there's a room about the size of this thing. It was just nothing but two cans, yeah. That was fun ride. Mount Sutro.
Oh, they're around the corner, you can't see them. I put that in today.
Oh, okay.
All the glass in the door to wall off that room. But right around there, there's four cans sitting on the floor.
Oh,
Next to
okay.
all the radio equipment. That's what we put in today. Just two glass panels and a door to wall off the mechanical. I mean, what do you call IT room or whatever. Yeah.
Yeah.
But yeah, there was four of those.
Yeah. So this has
Resonant.
a few other features here. So for transmit, you can actually modulate it. So it's got another, I'm not exactly sure where that is, but it's got a variable attenuator in the waveguide there, so you can modulate with audio. Oh. And let's see, there's another really cool thing in here.
Does this make sense to you? This is stuff you mess with.
Not as much.
Yeah, this is ancient. This is 1950.
Yeah.
Extremely clean though. It's just amazing how clean it is. Oh yeah. If you look at this waveguide there, see this guillotine that goes in there?
Yeah.
Oh, let me change it. There's a slotted line in there, the waveguide there, a very sharp edge there. And what that does is puts a lot of attenuation in there when you don't want to calibrate it, so you drop it off to a weak signal so you don't burn out the meter. And then you pull the guillotine out of the way and got full transmission. So stuff was very expensive in its day.
Oh, I'm sure.
And a few little mysteries there. So
Input for your
Few little
modulations
Yeah.
come here.
you can modulate, or it has internal modulation there.
Oh,
And then you have the detected output, so if you modulate it like you're running AM, then you can actually look at the audio that's coming out of it. Well, it makes a great 7 gigahertz transmitter. Unfortunately, we don't have a ham band that's 7
And not a 7, huh?
Not a 7
We
gigahertz.
got 5 and 10.
You have 5 and 10, yeah. Same as X band, this is H band.
Yep.
But this is extremely clean. I just can't believe.
Yeah.
For being from the 50s. Yeah. Looks like it was built to go in a tank. I mean, look at that case. It's
right.
stout.
Stout. But, waveguide, it's no different from here. Probes that we
This waveguide also.
That's all waveguide is.
It's connecting to other waveguides.
Yeah, that's a variable attenuator, so we can, this here changes the power level through there. So, all sorts of different layers. Yeah. Well, that's
So
very good measurement there.
What if we did like, what's the frequency range you could measure with this?
Anything that this is longer than a half wavelength.
2 hertz.
Half wavelength?
I mean, there's a point where there's like,
This has to be at least a wavelength long, half
Half
wavelength long frequency to measure.
Right.
So that's about 6 meters. So about 6 meters would probably be the
6 meters.
6 meters would be about the lowest frequency to operate.
Gotcha.
Huh.
We can go pretty much up to daylight.
Yeah, right.
Really?
Up to daylight. Yeah, it is. Do you see it
even touching.
No, it's just capacity.
You were
It
still-
actually works better with it. without
Yeah, I noticed it wasn't
past
so.
couple of years. That's less loading on the oscillator itself. So.
Truly.
I guess I should show a bird watt meter since that's now the modern standard for.
Is it? Okay.
Yeah. So again, the communications, this is the gold standard instrument for headwind standard ratio. This is the birdie watt meter. This measures flow and reflected power. This SWR meter is at low accuracy. And we have these various slugs for different frequencies and power ranges. So
Oh, I see.
rotate that, so measuring this way is forward power, rotate around and measure reflected power.
Ooh. It can tell.
You can tell it's directional couple.
100, 250 megahertz.
And so you will encounter a bird watt meter if you're in commercial radio at all.
Mm-hmm. Okay. So it's made for these ranges. Would you swap these out?
You swap them out, yeah. In the whole,
Would they,
these are full collection.
would a nano VNA also do this?
You would do some of that, yeah. These are now nano VNA is not certified with that.
Yeah, yeah.
But
It'll get you in the neighborhood.
heavy neighborhood where these are
It's
validated.
Check it out.
Sure.
Huh.
If you look at it's actually inside here. You can see
Yeah, that was my next question. Tear apart.
Here's the actual sample line in here. This is the center conductor of a transmission line. And inside here, there's a small loop that's either in parallel with this, and it's either parallel or anti-parallel with that. It's got a detector diode on here, and these are your connections here. That that just gives you DC voltage on the meter.
You say the loop.
It's just a square
Oh,
loop.
good.
Yeah.
Okay.
Inductive.
Wow.
I don't see those for sale very often.
You don't see birds? Oh, these are.
No, I don't recall seeing one. I look at QRZ almost every day.
Yeah. Well,
It's for
you see
sale.
around $400, but it's worth every dime, especially if you're working high powered. They're way you calibrate everything else off of.
Really?
Gotcha. That's the standard.
That's the standard.
Write that down. Bird watt meter.
Bird watt meter, yeah. It's Bird 43, type model 43. It's been made for about 75 years, and made a change. Okay, well now we know everything there is to know about RF, so let's go with some digital stuff here.
Hey, Joe.
Any questions before we move on?
No.
Okay, well,
I think I got a pretty, between the video and this demonstration, I have a pretty far better understanding of standing wave than I ever have before.
well, that's good.
I mean, I've been saying this for years and years and years, but I never quite fully grasped, right, what it all is. 'Cause even back in the CB days, we talked about SWR.
Yeah.
Yeah.
Which inspired my article, SWR meters make you stupid.
Which inspired your article, the CB days?
Funny.
But here's another excellent article. You've got a copy of this.
Yes, I do.
Yeah. Those have to be reading, required reading.
In fact, I printed that one.
Yeah, I'll just take a picture of that.
That's, yeah, I can send you.
Do you have some emails with you?
I might have that in PDF.
Are we having fun yet?
Would you be able to turn your board in this direction just a tad?
Take the glare off, maybe?
And I don't know if people can see
Well, if he
anything.
uses a dark color, we can, but if he uses a light color, no. Because I was watching a couple weeks ago and I couldn't.
We need a zoom lens on that thing. We'll eventually get there. Okay. So we're going to talk about the introduction to digital technologies. And this is all going to be a whole lot easier than anything you've learned so far. So.
Are you being facetious?
No.
Oh, okay.
Digital is either on or off. Okay. So, in digital technology, we don't really have to worry about too much about the inner workings of the stuff. We just work at the actual mathematical functions of what we have. So we start with combinational logic. And combinational logic is simple switches. Okay. So we have several different devices. This is called an AND gate. So it's AND gate.
Oh, and or.
Yeah. So if we have two digital states, okay, everything we do is either on or off. And if it's on, we have a 1, and if it's off, we have a 0. So we have an AND gate here. We have a 1 here, and we have a 1 here. And we get a 1 coming out the output. That's the logical addition. Okay?
1 and 1.
1 and 1. Okay. If we have a 0 here, we get a 0 there. Okay. So we both have to be on for 0. Okay. We have an OR gate, which is at the curved input. And if either one of these is high, then we'll have a high output. So we have a 1 here and a 0.
And then you got a 1.
And a 0 here, and a 1, and a 1.
Still,
And we have 0, and 0, and 0. Okay. Pretty simple. Okay. Again, you don't really have to worry about what's inside. What's inside isn't very profound anyway. And then we have it's called exclusive OR gate. And what an exclusive OR gate is if none of these are high, this is low. If one of them is high, this is high. If one of these, the other one is high, that's also high. But if both are high, then this is 0 again. Perfect example of an exclusive OR gate is when you have two switches on the light in your room. Okay, so if you switch, they have to be in opposite positions, right? If they're both up, then your light's off. Both down, your light's off. But if you're opposite positions, then your light's on. So that's a common example of an exclusive OR gate is a three-way
light switch.
Three-way light switch. Okay. We don't have to worry about. We're only talking about the logic right now. We're talking about any of the actual wiring or circuitry. Now each of these also has the negative of them. This little dot here, and something to the inside that you just reverse the output. So
This is the opposite.
you just take the opposite, and it's just whatever you would ordinarily have, that you just reverse that.
Okay. What would you call that?
This is we call a NAND gate, negative AND,
And, oh, okay.
and then this would be a NOR gate. And there's no exclusive NOR gate.
Right.
Doesn't exist.
Right.
Okay. Now, you can have multiple inputs on any of these gates here, but they usually don't. Usually 2 input gates are pretty much standard. That's why you run across a 3-input NAND gate or 3-input AND gate. But usually if you're using standard what we call TTL logic, you're normally not going to be using more than 3 of those, so you can make combinations of any of those.
Wow. This is a logic machine.
Logic machines. So
And you can line these up going, wow.
now it's called combinational logic because the state that we have only depends on the current state of the switches. There's no memory involved in it.
Right.
So we can make this as complicated as we want. We can take combination of AND and OR gates in there. So it's a combination. Take any kind of combination you want of switches that make something work, you know?
Yeah.
And so, but we don't have anything that tells us what the previous state was, so there's no memory involved in there.
Right.
So once we get into memory, then we have it's memory logic or
Right.
sequential logic is an official name for that. So we mentioned that we went into a flip flop a couple of weeks ago. I can't remember how we got into that, but we did.
Yeah, I remember what that was.
Take two transistors and connect them back to back. That, cross connect them. And over here, we take the resistor from here to there. We take the resistor from here. What this will do is, whatever state this is in, this transistor will be on and this will be off. And so we can toggle them and switch the state of these. But only one of these transistors can be on. So if one transistor is on, it forces the other one off. And if we turn the other one on, it forces this one off. And so it's called a bistable. We can have two stable states. Now, what we can do is we can trigger each of these with a negative pulse here, and a negative pulse over here to change state. So if we want to flip, and the designation for these is Q and Q prime. So Q means this one's on, and Q prime is the state of this one. So the Q and Q prime will always be on opposite. So whatever Q is high, Q prime will be low, and vice versa. Now, here we need to trigger them from two different sides in order to make this thing work.
Right.
So
At the same time or separate times?
Separate times,
Yeah.
yeah. It's a great
Yeah.
toggle switch. Okay, toggle switch is close to what we have here. So what we would normally use this with is here. And so if we put a pulse in here, negative pulse in here, whichever state it's in, it will reverse it.
Because it's going both
Go to
sides.
both of them. The one that's already on, it won't have any effect on at all because it's diode reverse biased. The one that is off will now turn on because this diode will not conduct. So this will respond to whatever is not on will respond. Whatever is on doesn't care. So as we put a pulse here, every time we put a negative pulse on here, this is going to change states. So this is your simplest memory device. This is your fundamental unit of memory, a one-bit memory.
That's 1 bit of memory.
1 bit of memory.
So controlling it,
Is a
Just
sharp
a
negative
pulse.
Negative pulse.
And did you get a reading out of that somewhere?
Yes,
Is that what
we
comes
read
up
the
top?
voltage at the collector of these transistors here.
And
and
it'll tell you-
it's either going to be on or off.
On and off. And both the Q and Q prime are always going to be the opposite. Now, the nice thing about this is if we're looking for, every time this changes states, we'll get a negative pulse out of here. So we can see that every time, or for every 2 pulses here, we get 1 pulse out of here. So it's a 2-to-1 frequency divider by itself.
2-to-1 frequency divider.
Because the pulse will go out the other one.
Yeah. So every time you hit a pulse, it will change state. Then
So the second pulse is going to go through the other one.
We'll also get the same thing. These will both be half the frequency of that, but of different phase. So 2-to-1 frequency divider, and your most fundamental memory unit. So you talked about gigabits of memory. You've got gigabits of cross-connected.
How fast would that be? I mean,
Fast.
like, so when you say
Oh,
frequency
pico-
divider, you could like go to, if you get something that's 20 kilohertz and you put it through there, it's going to be 10 kilohertz.
Yeah.
On one end.
I'm on it. Well, it's actually both, but they're both going to be out of phase.
Yeah, phase.
Right.
But,
So you could detect the average frequency or.
Well, not the average, exactly, it's exactly half of what you put in. So if we went by 4 to 1, we just take 2 of these and cascade them.
frequency divider.
Yeah.
Ah,
And the actual switching time is in the order of fraction of a nanosecond.
Yeah.
And it's real high-speed logic can be down in picosecond region. Doing your microprocessor.
Yeah.
You'll have, millions of these things in the.
And that's, you said that's, those two are transistors, right?
Yeah.
Okay, so they're.
you said millions of these in like a calculator, or your phone, or any memory stick.
Whoa.
Now, this is volatile memory. There's also non-volatile memory, which works entirely different. These require that you have power waves applied, or otherwise it goes away.
Right, because you can shut that off.
RAM.
Shut it off and
Boom.
so,
It's there.
so, yeah, we won't go into non-volatile memory here at this time, as I mentioned that it exists. So, we want to go to combinational logic or sequential logic, and well, let's see. Okay, how do we divide by 10?
How do we divide
Divide by 10.
divide by 10?
Mm-hmm.
Well, you could have 5 of those devices, or that would be half. No.
It's not easy. It's easy to divide by 2, it's easy to divide by 4, easy to divide by 8, easy to divide by 16,
Ah,
okay, easy to divide by 32.
2, 4, 6, 8, 6. Right. But
So what we have to do, this is going to nearly be 2, 4, 8. This be 8 to 1 divider.
Mhm.
And what we have to do is we have to have a suppression pulse in here. So we have feedback in here, so suppress it, so we can suppress two of these, and then we finally allow the next one to divide there. So if it's not a power of 2, your
Right.
frequency dividers become very complicated, because then you have to do this Texas 2 step in between to do it. So that's why we have things like JK flip-flops, which actually have a clock input as well, so you can suppress them during the cycle. So there's ways to get doing all this. So, but for now, let's talk about the importance of binary communication. So since we're all working with powers of 2, this is kind of dictated by the simplicity of a flip-flop, okay? So we divide by 2, divide by 4, divide by 8, divide by 16. So we have this binary counting. Okay? Let's see. There's 10 kinds of people in the world, those that know binary and those that don't.
Right.
Okay, so so we have placeholders, or we have place value for binary, okay? So here's a ones place. Here's our 2's place. 4's place. And here's our 8th place. 16th place. 2 place. And those are computers now are 64. We're just processing, okay?
Ah,
Okay, so how would we write the number 7?
8 minus 1.
Well,
2, 3, 4,
If
5,
we have a
6, 7, 8,
64-bit machine, we have to use all the bits, okay?
Oh,
Wait,
So that-
4?
This is a 64-bit machine.
yeah, you have
So
to
we
use
have to use
all
all
of
of
them
them.
to make a 7.
Yeah. So
Okay.
0, 0, 0, 0, 1, 1 plus 2 plus 4 is 7.
Huh. Okay. I see.
I don't have a clue what you're talking about right now, but I'll just keep watching maybe.
Well, you're simply adding.
Well, I get the
numbers to
math,
place.
but what is 32? I mean, what are we counting there?
What we're doing is this is the binary place, so any number that we have, anytime this would be a 1, that would be represent
It would
32.
equal 30.
32,
Uh-huh.
okay. So what's the highest number you can count to with 64 bits?
Just add all of that together,
Or the-
and that would be the highest number you can count.
Mhm.
If they were all ones across the top.
Yeah. So it actually go 127 because 0, you always start at 0.
You always start with zero.
You always start at 0, so 0 to 127.
Not 128.
No.
127, because 0 is a number.
0 is a number.
Uh-huh.
So this is how a 64-bit processor counts
Yep.
numbers.
Right.
With ones and zeros.
Yep.
Either on or off,
On or off.
and spits out numbers.
Yep.
Which could be encoding video, it could be
Could be anything.
anything you're doing and that processor is working on inside the computer is doing it through that.
Multiple of them, and then adding
All
and
the
subtracting
time,
again.
Well, if
Binary arithmetic is,
if your processor speed is, I don't know what's a processor speed today,
well, 5 gigs.
5 gigahertz processor, so it's counting 5 million times a
Well,
second.
5 operations.
Five operations.
Floating point operations, so we have to do running floating.
Sorry, I'm asking so many questions. I
No,
really
no,
don't know
yeah.
anything about this.
So that's how many times this shift register is done, number crunching it, so there's a cycle.
Per second.
Wow.
Yeah.
Okay, so it's a lot.
It's a lot.
Yeah. No kidding.
Now, what was the first digital communication system around?
The first digital communication would be Morse code.
Morse code, yeah. Now, Morse code is kind of semi-digital, because we really don't have, we've got actually a variable rate. So that's part of it.
Short, long, on, off. Yeah, I mean,
Actually, it's a baud code, teletype. The teletype, which is a 5-bit code.
oh wow, teletypes.
Teletype, yeah. So we still use it, right? Use Android.
Really?
Yeah, really. And so that uses a 5-bit code. And the way we figure out how many characters are available is simply 2 to whatever power that is. So 2 to the 5th power, which is what?
Is it 16? 1, 2, 4, 6, 8. 2, 4, 2, 8. 32.
That's actually comes out to be 32.
32.
Because you have to
The
count
number
0 with all the
32.
zeros there. With all the zeros, yeah.
You have to
Oh,
count
you count
zeros.
zeros.
Yeah.
Wait, 2. Wait. We start with 1 or 2?
Well, let's say we start with 0.
0.
1, 2, 4, 8. So let's see.
8.
2 to the 5th. 2 to what power is 32?
2 to what? 2,
2 to the what power is 32?
8,
Is
16, 32 to the 5th.
yeah.
Yeah.
Yeah. Okay. Yeah. So we have the capability of 32 characters with a 5-bit code, 5-bit code, which was baud code.
Odd.
So, if you ever worked with old teletypes, you always say, why are you yelling all the time? Because you only had capital letters there. You didn't have enough, so you only had enough code to do capital letters and a couple of control signals.
Numbers or signal, yeah.
And so if you wanted numbers, then you did a caret shift, and then you got another, you were able to duplicate that again, and you got a few other control characters, that sort of thing. So the standard teletype machine had 8-bit, 5-bit, 32 characters capable.
To this day, I have never physically looked at a more complicated machine than those big teletypewriter machines. With the moving parts and the levers.
I used to maintain them.
Holy moly.
Want to see a great video?
Wow. I could not, that's the most complicated machine I've ever seen in my life.
He's got a great video on it.
Wow.
Yeah. All you yeah, I should use.
Yeah, that,
They still use
Really
those when I came into the Air Force.
are they?
When I came into the Air Force in '84, they were still using them.
Really?
Yes,
Mechanical.
Yep. mechanical teletype. Yeah,
Yeah.
Model
The fact that it's moving that plate around
Yeah.
all the time, it's like,
Model 28 locomotive.
yeah.
They spewed a significant amount of oil. That's the other thing called a reperforator, which generated confetti all over the place.
yeah. Yeah, we were still using the IBM 80 card column.
Yeah.
Go to the computer room. The computer room was the size of this and did about this.
Uh-huh. Wow.
But that was teletypes. The first time I laid eyes on one, I was just like, that is a marvel of engineering.
So what's it?
I bet they need a lot of maintenance, because
How many bits is a standard communication code now used for, not the processing, but for communication between terminals? What's the standard code now used for computer?
I'm not sure which
That is, that allows you all the letters of the alphabet plus all the numbers plus all the punctuation.
128.
128, it's the ASCII code.
Why do I know that?
Because it's your standard ASCII code. Yeah, standard ASCII code is 128 bits.
Okay.
So. Well, 16 bits, 128. Plus the characters. Okay, so how do we convert this into actual communications?
Yeah.
Standard teletype is what sort of modulation?
What sort of module?
Yeah,
Analog.
No, it's is it three? I mean, do you basically have three positions, or is it? I'm trying to remember.
actually two.
Two positions still?
Frequency shift keying.
Frequency
There's a
shift.
mark frequency
Yeah.
and a space frequency. So
Huh.
you'd have a carrier out there, and for every time you had a mark,
Yep.
a zero, you would shift one frequency, and space would be the other frequency. And so you have a spectrum that looks kind of like this. Now, when you're keying very fast, the spectrum actually starts, if you look at a spectrum analyzer, starts having something like this. As you're turning it on and off, you have sidebands in each of the
Right.
frequencies. Actually, it's closer to FM. So you have all the FM sidebands. We were talking about whenever FM modulates something, you have an infinite number of sidebands.
Really.
Well, basically, when you're shifting this thing instantaneously from one frequency to another, you have a huge amount of bandwidth in terms of sidebands. So.
Oh, so it's not doing a little 3 kilohertz. It's
No.
Wide
Yeah.
is it? Okay.
Yeah. So frequency shift keying was the first digital communications mode, and then nowadays we have all the stuff that we use not only commercially but amateur. We have multi-frequency, both amplitude and frequency modulation at the same time, amplitude, frequency, and phase at the same time. So that's pretty complicated when you start working with higher level modulation schemes. But it was all started here with the frequency shift keying, and it's real easy to do. As a matter of fact, a very interesting lady by the name of Hedy Lamarr invented frequency shift keying. And she was using piano rolls with different holes there, which would, each of those holes there would key in a different capacitor and an oscillator. Yeah, we were talking about oscillators, like a hardware oscillator. And the frequency was determined by this frequency here in this tank circuit, let it oscillate. And so if we have a whole bunch of different fixed capacitors here of different values, and we connect this thing to a piano roll, and it changes the frequency by different amounts there. So, so that was Hedy Lamarr, the actress who invented that.
Really?
Pretty cool. Now, the only thing you had to do, you had to have another piano roll that everything was synchronized, but she figured all that out.
Frequency shift keying. FSK. Yeah, it's coming back to me. I remember taking my general test now. I forgot about that.
Now, since we're on that subject, and there isn't a whole lot on the commercial license, but there's quite a bit on the amateur license. Did you talk anything about single sideband, or very much about it?
Did we,
Yeah.
when Kevin was here, I mean,
No, when I had my little doubly balanced modulator here, and I showed you how to do modulation.
that's the night I wasn't here. I
Oh,
tried
that's
to
why
watch
you
it,
weren't
and,
here. Okay.
and you left the camera aimed that way when you guys were over here. So
Oh.
I got bored real quick. I was sick.
Okay. That thing up there is a spectrum analyzer, okay?
Right.
It shows you amplitude versus frequency, whereas the oscilloscope shows you amplitude versus time. Okay? So if we were to take a standard AM carrier, or AM signal in broadcast, okay, you have a carrier frequency, which is what your license frequency is. Keep all the numbers nice and round, so 1,000 kilohertz, okay, or 1 megahertz. Their carrier frequency, and we're modulating this with a, let's say, a 1,000 hertz tone. Okay, pretty boring program.
Yeah.
So what we have, if we fully modulate it, we have 2 sidebands, which are, how far are they separated from the
On AM, it's
so
a,
for a 1,000 hertz tone, it's very precise.
oh, I'm sorry. I thought you were talking about the whole
No,
signal.
with the signal,
Just the carrier.
just a carrier and one modulating frequency.
I think it's less than 1 hertz. I mean, it's
So
a
if
Depends
you
who
have
kind of
1,000 hertz, once the sums and the difference. So if you have 1,000 hertz audio going in here, we're going to have 2 sidebands. One's the carrier plus 1,000, and this is going to be minus 1,000. Okay. If we call the center frequency F sub 0, is our upper sideband, and here's the lower sideband. Now, if we're using voice or, lead audio, then we've got a whole bunch of these sidebands happening.
Just because they're going out sideways. Yeah.
But for any single frequency, we always have 2 sidebands, and they're separated by exactly the frequency of the modulation from the carrier.
Well, you always have 2, but
You
there
always have
could be
2.
more.
There can be more. Well, for AM, if everything's linear, you're only going to have 1 pair of sidebands for every
Oh,
modulating frequency.
okay.
So if you're modulating for between, 20 hertz and 10 kilohertz, which is typical AM, not real high fidelity music, but
Right.
medium fidelity music, the higher frequencies are going to be
So
customized.
why do you have a carrier frequency for AM and not FM?
You do have a carrier frequency for FM.
But it's silent, is it not?
No,
No?
no. On AM, the carrier, that's where all your power is really modulated. Right?
Huh.
Okay? That's where the carrier frequency is.
Okay.
On FM, you have a carrier frequency as well, but when you put modulation on, you're shifting the frequency as opposed to shifting the amplitude. So on an FM, and AM, you're doing this,
Yeah.
and FM, you're doing this.
Yeah.
Okay?
Okay.
So you got a frequency, and you're shifting the frequency on FM. The power stays constant. Whereas AM, the power is added, your sideband power is added.
Oh, yeah.
So on a, let's say 50 kilowatt transmitter, you got 50 kilowatts of AM per carrier with no modulation at all. And when you modulate it fully, you have another 50 kilowatts in the actual sidebands.
So I guess I didn't ask the question correctly. If I'm in upper, or we'll say lower sideband on 40 meters,
Yeah.
and I'm scanning around, I come across an AM station, it's squealing. I mean, it's
Oh, sure.
loud.
Yeah.
Because it's trying to
Well, no,
modulate.
what's happening is you've got a carrier on a single sideband, you don't
Yep.
have a carrier. You suppress the carrier.
Right.
Whereas if you tune across an AM broadcast station with your
So
phone still
I'm
on there.
picking up that giant carrier.
Yeah.
Okay. I guess that's what I was trying to ask, because of course we use single sideband all the time. So you drop your carrier.
You drop your carrier and you drop the opposite sideband.
Uh-huh.
But in order to demodulate, you have to add the carrier back in. That's where your VFO is, or your product detector.
Which is why it's just squealing in on your,
Yeah,
okay.
but that's your exactly zero beat. if you zero beat the carrier.
Sure, then you can actually hear voices or music sometimes, yeah.
So, yeah, we have a AM broadcast, we got all those audio frequencies between each 20 and 24 or whatever, and that all sideband. Or they're gonna be perfectly symmetrical, so symmetrical groups of sidebands. Now, in FM, we mentioned that you have sidebands as well, but rather than having a single pair of sidebands for every modulating frequency, you have an infinite number of sidebands for every modulating frequency, and those are spaced. The spacing between them is equal to the modulating frequency. Now, the loudness of FM, the equivalent to loudness, the greater modulation is how far you swing that frequency. So if you swing it just a little bit, it's going to be very quiet when you receive it. If you swing it like large excursions in frequency, it's going to be louder in the receiver. So that's your deviation. That's what's. But the total power on FM is the same. Now we mentioned that it's very one of the real advantages of FM is we can amplify with Class C amplifiers. They don't have to be linear at all. All we have to do is amplify the daylights out of them, and it doesn't have to conserve any amplitude information whatsoever. Because when you receive it, you lop off all the amplitude information in the first place. All you're left with is what's happening in between the crossover points. They don't really care about the frequency. So in single sideband, you basically, if you have about a 9 decibel advantage over full carrier AM with a single sideband. All other things are being equal. So that's if you include the receiver and everything put together, it's about, it's equivalent to having like 10 times the transmitter power over AM.
Huh.
One of the forms of single sideband was actually quite popular a while back. I don't think it's used too much. It's called ISB independent sideband, where you actually have a full duplex. You would have transmit on one sideband and receive on the other sideband. And so you have both the same carrier frequency, so one guy would transmit. But the neat thing about it is you didn't have to switch between transmit and receiver. It's full duplex all the time, so there's no switch over between one and the other. So.
You said that the on FM, it's the carrier frequency for the steps. I'm sorry, I'm trying to grasp what you were saying. On the carrier frequency on FM, the steps are based on the frequency.
Yeah, well, the deviation.
The deviation
on the loudness.
Is based on. So if you're high on the FM band versus low on the FM
no,
band,
that's constant. Yeah.
Okay.
This is for a given.
That's for a given
frequency or a given service. Now, FM broadcasting is very wideband. It's a deviation of 15 kilohertz either way. Whereas for 2-meter radio, it's 2.5 kilohertz.
Right.
So we can even going less like 1.5 kilohertz on some of the what they call sliver band radios. And if you want to convert a wideband radio to narrowband, you just turn your microphone gain down and automatically turn narrowband. But then your signal to noise ratio goes down the drain, so then you have to make sure you compensate for it. So you talk a little bit of phase lock loops there, which is kind of a neat combination, interface between analog and digital. Let's see. License manual on sequential logic. Oh, hey, I want to give an example of sequential logic. Dial telephones, okay? I don't know, some of you guys don't believe what a dial telephone is anymore. But what you had is when you dial the dial.
Rotary or tone?
No, the dial.
Rotary?
Rotary, yeah.
Okay.
What you did is when the rotary went around, you had a relay that closed for every time it went around, it closed the contact. What that would do is it advance a stepper relay to the next step. So you had this, like a distributor, with a stepper relay, and you have this set of contacts around here, and you have it advances thing to the next one. And then your next dial, this would be in some other city, you know, and then this do the same thing over again. So then you have another set of contacts, another set of contacts, another set of contacts. And then each one of these would go to another city or another state or whatever. So you have to, you know, set 7 numbers, you know, so you go through 7 different offices, you know, so each time, each number was a different office that it went to. And then, so that's how you got to the final destination. So this is actually base 10 logic, which is not very easy to do with flip-flops, but with mechanical relays are easy.
Or you just dial 0 and talk to the operator.
Yeah.
I remember that.
Let's see.
I'd like to make a collect call.
You know, there's actually videos kids are making these days on those, like Instagram and TikTok and whatnot, where they're talking about how it's like, man, you know, it'd be a really great idea if there was just like one phone in the house for our whole family to use.
Right.
I'm like,
I was on a
wow, I feel really old right now.
I was on a 4-party line when I first moved up here. I'll run across it when I'm not looking for it, but I had a couple of 10 volts stuff relays.
So those open wires that used to go between here and like Valdez.
Yeah.
Just open line
They're
wires.
still there, yeah.
Yeah, some of them, that's for those insulators.
Yeah.
That was one of these points. It would just shoot down to Valdez.
Yeah.
And you'd be
Maybe another.
talking on those open wires. Until they put that Moran station in. That shut that down that
Anyway, that's perfect example of sequential logic. Because this doesn't happen, nothing happens here until this is done, you know. So
Right.
Just like that. So very, very simplistic, very old way. By the way, back in the 1924 AT&T book, which, by the way, was one of Dad's, and they were doing frequency or time division multiplexing back in 1924 using spinning commutators. So you have 10 lines coming in, and this commutator would spin around really fast, and they have a synchronized commutator at the other end, just like a distributor around a car.
Yeah.
The thing would be spinning around really high speed, and the signal coming in would be divided into that, and then sent down the line there, so you had all these conversation on a single pair of wires, which was separated by time slots. And then they were sorted out later on, so just like the bigger comb filter. You know, each fraction of a second would be a part of the conversation.
Only you're listening to that.
Yeah.
You wouldn't hear the rest of
You would hear the rest. You'd only hear the one.
How quickly those things have to be.
They must even
They were
spin.
screaming fast.
That's what I'm saying, man.
Yeah.
Otherwise you hear.
You'd have to have like 30 pulses per second or something.
Well,
Yeah.
the Nyquist sampling criteria, which will when you go into digital communications, you only have to sample 2 times at the highest frequency per cycle. So when we were doing audio sampling there, the sampling rate doesn't have to be any higher than twice what the highest frequency is. So that, you know, the voice frequency or telephone frequency or high frequency is about 2,500 hertz, you know. So you only have to sample at 5,000 hertz. So that's almost doable with mechanical devices.
Yeah, a lot of those connections weren't clear either.
oh yeah.
You had to yell in the phone sometimes.
Right.
I mean, you could hear the.
I remember that, yeah.
So, which brings us into analog to digital conversion. How do we do it? Okay, there's so much audio there, that's the A to B converter.
Well, you showed us a sine wave early on, and then you showed us a blocky sine wave,
Sampling.
sampling the.
So, what is that thing by itself?
What is that thing by itself?
Trans.
Is that, are you rectifying or?
No, what's the symbol of triangle always symbolize?
Amplifier.
An amplifier. Okay?
Amplifier. That's what it
So if we have an op amp, normally we have negative feedback, right? Building an op amp circuit.
Yeah,
I remember we built this.
I do recall you saying those words.
Oh, negative feedback. Oh,
Yeah,
yes.
yeah,
Right.
right over here, yeah.
And the
Call
gain
it
of that
negative
is a ratio of R2 to R1.
Huh, uh-huh.
Okay? And we always use negative feedback to make this thing stable. Okay? If we don't have any negative feedback, it it's gonna be an unstable condition, it's gonna flop from one side to the other, depending on where our signal is. So we have what's called a comparator, which compares an input amplitude to our output amplitude. And, next week we could probably go through this, so. So we'll set a reference voltage here, but let's set a reference on our negative voltage here. And we'll use 5 volt TTL. 5 volts is pretty standard voltage for any digital logic or years around. And this is a 10K resistor, and that's a 10K resistor. So what's this voltage going to be here normally at this point?
Infinite. 0.
Well, yeah, 5 volts
Five.
here, 0 here. What's that going to be there? When you have 2 equal 5 resistors, what's the voltage in between?
It's the same. No?
It's going to be half your supply voltage.
All right.
Or the 2.5 volts here.
Oh,
But it's 2.5 volts anywhere on that line, correct? Or just
anywhere between.
Anywhere between.
arbitrary between, okay.
All right, I was
Okay.
wrong. I was thinking of the.
And now we don't have any negative feedback, or we want to use the semi-unstable part of this. So we put a sine wave in here. Anytime the sine wave goes above 2.5, this end goes high. And anytime it goes below 2.5, it goes low. Okay? So it's a sine wave to a square wave converter. Or analog to digital. Okay? You either have a 1, we either have a 0 here, or we have a 1. Okay?
Right.
So it converts from 0 to 1, and where that is. Okay?
Analog to digital.
Analog to
And
digital.
if your sine wave is very fast, you're going to turn it into very short pulses.
We're circles in.
Okay.
So exactly the same for that.
And if your sine wave varies in frequency, then your pulses are going to vary in frequency.
Right. So we have, this is a one bit analog to digital.
1 bit.
Yeah. Now what we can do, if we want to do what's called a flash A to D converter, we want to convert a analog voltage into something more than just a 1 and 0. We have a whole string of comparators. And so this will here, 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 that round positive 5 volts. And then our inputs are all going to be tied together.
Input, okay.
And then this is going to be our input signal. So what it's going to do is we're going to have a chain here. So as our input signal, each of these is 2.5 volts, right? Across each one, we said. So as this signal goes in here, blah, 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 divided by 5 to 1. So it should be 1 volt here in this case. So as this exceeds each of those voltage, these are going to fire sequentially.
Oh, it's like we're sampling at different,
Yeah.
oh, wow.
So it's called a thermometer A to D converter. So if I put an LED on here, it can tell how much voltage there is by how many LEDs light. Now, the disadvantage of it, you don't have very much dynamic range. You only have as many bits as you have here. So these four bits, you know. So what we need to do to make this thing more versatile, in other words, handle very large ranges of signals, we have to encode this. So rather than having just 1, 2, 3, 4, this would be 1s, 2, 4, and 8. For power, we could do a binary conversion on each of these. So rather than just a sequential addition, each of these will have a place value. So this would be our 1s, this would be our 2s, these would be 4s, these would be our 8s, and then we can get a huge range of, we can get 16, 16 different steps that we get that.
2, 4.
1, 2, 4.
Well, 1, 2, 4, 8.
Yeah, 50, yeah, we can have 0, remember 0 is number 2. So
Wait.
15 possible steps.
Okay.
So this would be our 8 places, so that we have them all 8 plus 12. 8 plus 4, 12, 14, 15. So it's written all on.
Mm-hmm.
So we have to have some coding circuit to do that. So you need a little more components in order to do that. That's your standard, what we call a flash converter.
Huh.
Now, when we're sampling audio, what we want to do is we want to do that really fast.
Right.
And we want to do that with enough resolution so that we don't lose big chunks out of the audio we have. So if you want a
Analog to digital audio converter, okay.
Wow.
Let's make a DVD out of a record.
So we have a wave like that, and we want to reproduce that with digital steps. We're going to have something that looks like this, right?
Mm.
So we want to sample this thing as fast as we possibly can. We want to make these steps as small as we possibly can to make this, get the best reproduction of the flavor here. Now, there's this very important factor called dynamic range. Okay, it's the ratio of the smallest step you have to the largest step. So if we have 16 bits, what's going by binary, once again, we're going to get right back to decibels again, okay?
Oh, okay.
So, yeah, let's talk about 16 bits, okay? And 1 bit is the smallest amount of information we have. So, what's the highest number we can count with 16 bits?
256,
Okay,
is that right?
that sounds right. Good. Okay, so what's the smallest?
I'd have to do that math.
0.
0.
No, it's actually one of the smallest bit. Okay. 0.
Oh, okay.
So we have the smallest count. So I have 256 over 1, and so what's our dynamic range, or what's our decibel ratio between those?
dB equals,
Now,
Oh.
one trick here is this is voltage, not power. Now remember that voltage stuff.
oh, okay, never mind.
B.
dB in volts, or dB, if you're looking at voltage, is equal to 20 times log for power.
Right.
It's a 20 times log
Really?
of V1 or V2, 256,
dB volts.
6 over 1. Okay, so what's the, so what's the log of 256?
Yeah. You've already demonstrated you're going to be the only one.
Yeah, well,
Just- You lost me at equals, sorry.
Jill's a lot smarter than I am, by the way. She's good.
256, and then times 20.
That's funny, yeah.
Okay, so we're at 48.
48,
Point
okay.
2.
48 dB of dynamic range.
Wow.
Okay.
Okay.
And 48 is almost 50 dB is 100,000 to 1, okay? 50 dB is 100,000, okay?
Okay.
So basically, if we want to look at the different power levels here, we between the smallest and the largest that we can hear.
It's going to be
is
48 decibels of dynamic range.
Yeah, or about 100,000 to 1
Wow.
ratio of power. Okay.
That's pretty good.
Yeah, that's actually.
But keep in mind that the threshold of human hearing, if you've got decent ears,
Oh, okay.
nominal
Yes.
hearing, 1 dB is the threshold of perception, okay?
Okay.
The threshold of pain is 140 dB.
Yeah.
Oh,
That's
So it's
So
like-
how much, what's the power ratio between barely hearing something and going deaf?
you said 100 and what?
140 dB.
That's a
Threshold
lot.
of pain, which is, that's the level at which you can't hear any difference in the level. You're basically saturated. So what's 140 dB in terms of power ratio? We can go backwards.
Same thing, or are we multiplying
Well,
times 10?
this way we'll keep it in power, okay? 140 dB is power, okay? So we'll go backwards. So remember dB is equal to 10 times
10.
log
Yeah. Log of,
of power 1 or power 2. So we want to go backwards. So 140 dB, we divide by 10.
yeah, 140.
So we have 14.
Oh, wait a minute.
What we're trying to do is find out this power ratio here.
Right.
So we
Oh,
have
right.
dB. So you have to start with 140.
Okay.
and
Yeah,
we-
so 14.
So the 14. So then we take the anti-log of 14.
Oh, I don't have it.
What's
You had it.
yeah. 10 to the x. Okay.
The antilog of 14.
Yeah.
Yeah. 10 to the 14. Right.
Tens, hundreds.
Yeah.
1, 2, 3, 4 commas and 100.
4 commas at 100. That's 4 after that.
So 100 and then 4 commas afterwards.
I don't know if the comma would be there.
Oh,
That
oh,
European.
four. Oh, yeah, oh, okay, so that's
Then 3 zeros, comma, 3 zeros.
hundreds,
Is that what you
thousands,
said?
Billions.
millions, billions, trillions.
100 trillion. Okay.
Okay, that probably sounds about right.
Yeah.
So basically, the threshold of pain is 100 trillion times the power of the weakest detectable sound.
Wow.
That's the dynamic range of the human ear.
Trillion.
That's
If
huge.
you have any ear left.
Well, I guarantee you mine isn't.
Pretty amazing, isn't it?
Yeah,
That's a wide range.
We can,
that's quite the detector we've got between our ears.
unless you've been using
Using-
pods there at 1 watt for.
Yeah.
Or around jet
Many
engines
people are.
and guns and, yeah.
Yeah.
Mhm.
Because I've always worn my hearing protection. Every
Yeah,
time
sure.
Every shot I got.
Yeah,
Ever.
me too.
I wish I had when I was in my 20s.
Yeah.
I made some dumb.
Train how you fight, right?
Right,
You're not
right.
gonna have your protection up there.
We're doing test well.
Totally.
That's a lot of ratio. Power ratio.
Wow.
That's why high fidelity, high end audio is so important to some folks because they can really hear the difference between
Wow.
a poorly made record and a very there's different qualities of records.
Oh, yeah, definitely.
My neighbor used to get white ones because he said the black ones were just colored black to hide the impurities in the vinyl.
Well, that isn't really true. They usually
That's
carbon
what
black, they cuts down on the static too.
Yeah.
Huh.
So we're sampling this stuff and we want to put it back together at some point, right? So how do we convert a digital pulse into an analog signal?
Like to put it through a speaker, say,
Well,
or
to an analog.
Digital
anything.
analog.
How do we get from digital back to analog?
Yes.
The thing with the 8 prongs on one side and the one going this
Yeah.
I can see it, I can't name it.
Well, it's called a D to A converter, but what's the, going back, you remember talking about the 1-bit A to D converter?
sure.
Right,
Which is just a comparator, okay?
right.
What's a D comparator look like?
Capacitors.
Very good. It's an integrator, okay? So an integrator, if we have a square wave coming up, okay?
So that's a resistor and a capacitor.
Resistor capacitor, yeah.
Huh.
And you have a square wave going
So
into
again, this is going to average it to the midpoint of that, right?
Right.
So it's an averaging circuit.
Over time.
Yeah. So If we have a whole bunch of analog stuff, we can actually just, it's simple to convert back to analog.
That seems ridiculously simple.
It is ridiculous.
Yeah.
Now, it's not the most elegant way, but it will do it. A lot of stuff we do, you can do crudely and do
What's it called again? An integrator.
integrated.
So all you're doing is just slowing down the,
Yeah,
where the voltage
Yeah,
spikes on that square wave.
yeah.
It takes time to do that.
It's time to do that.
Because you're gonna slow down the move.
But this is gonna happen really quick. I mean,
Yeah, well, and,
but you are slowing.
yeah. And so there's several ways of compressing the audio into here, and we were talking about compression for all sorts of things. Because of the huge dynamic range here, you don't have, it's really hard to get 140 decibels of dynamic range, as we showed. So
Yeah.
60 bits,
Huge.
you have 250. So there's mathematical ways of using what's called more significant bits or least significant bits, where some are more important than the other ones. So when you decode it or encode it, you can, if you take out the most significant bits, it's going to be trash. If you take out the least significant bits, the fidelity goes up a little bit. But, so we're just deciding, making a judgment call on what bits are more important for us to hear. So you want them all if you can get them.
Yeah.
Everything's a compromise. But
That would be the difference between something that's sampled at a much slower rate
At a
versus
slower rate,
lossless,
right.
what they call lossless,
Right.
but it's,
yeah. So you want to sample it at least twice the Nyquist sampling theorem is twice the frequency of the highest audio you have in here. So if you've got 20 kilohertz at the high end, you want to sample at least 40 kilohertz. The standard CD is 44.1 kilohertz sampling, which is just barely adequate for a little slop over to sample to 20 kilohertz, which is considered the high fidelity.
And you wanna do twice because of this right here?
Not really. The sampling theorem it's really kind of bizarre if you look at the math in there.
Okay.
It's called Nyquist sample theory, and there was a whole lot of very smart people coming together to actually come up with that. You can look at Nyquist.
Yeah.
so there was most significant and least significant bits. Would a least significant bit be one that would
Like
be?
the ones in the twos place, and the
Right.
most significant would be, we got here 64's place. So whatever.
Ah.
Now, if you've done any number crunching on the computers, or you've probably heard of big endian numbers and little endian numbers, whereas when you do the number crunching, whether you have the big end
Right.
go through a computer first or low end, and it's faster processing if you do the most significant bits first, and do the other stuff later. But then you have to usually convert it so that when it's finally done, you have to have a little endian, little endian numbers coming out first. Later. Let's see. I think what more to say about that. Read the book.
So DMR would be like taking an analog signal, converting it to digital, and then sending it from airwaves.
Yeah, and there's, like I say, there's all sorts of different ways you can modulate it. Most of these kind of things are using combinations of amplitude and frequency modulation, and usually multi-tones, which are also. Gates.
I'm amazed.
You could just live in those two books.
That antenna book is freaking amazing. That is,
Yeah.
you can
You really live in
lost
that
in
world,
that.
right?
Yes.
Right, that's what I'm saying. And those are both the same, right? The black one and the yellow, they're really the same.
I don't
Right.
know. I don't know. That's 2018. They just came out with a new one. I didn't buy it because I think I got it in the amber one there.
Right? Pretty much the same thing.
I think.
They just come out with a new version every year.
Well, not every year, but yeah, they update it, put some new articles in the front.
Oh,
Most of the information
doesn't change.
doesn't change.
Yeah.
American Radio Relay League.
So if you have your book there on page 134, it shows analog digital sampling here. You can see the different codes.
That's my book, so
Oh, that's your book. So that shows a sequence of numbers
steps.
again.
Yep. And then it turns it back into a sine wave. Or
In
close
analog,
proximity.
yeah.
Yeah.
Okay. That's probably as much digital stuff you're actually going to get on the test there. You want to know what the truth tables are for the different logic states. So page 126 here, we have the truth tables, for example, 3-input NAND gate, and for every combination of inputs, what is the output there? So
Right.
you want to be able to do that stuff
In your head.
pretty well.
Okay.
Which is not rocket science. Just ons and offs, yeses and nos.
That's on the test.
That is on the test.
Definitely. Three input.
A 3-input NAND gate, and again, most of your gates are going to be 2 inputs,
Right.
but it does give it a logic state for it.
Where did they get the word gate from?
Well, it's electrical gate.
Is that it's literally just that?
Yeah.
So, for example, no, now, most gates that we work with are actually inverting gates because the transistor, if you look at the input to output voltage, is always going to be inverted, right? Class A amplifier, you're talking about class A amplifier. So if we're looking at you have a dropping resistor, you have a collector here, right? And this is that ground. And what happens as we move the base voltage up, what happens to our collector voltage? Collector voltage.
Is that voltage, that one would reciprocally go down, I would
So
say?
yeah, because if we don't have a voltage here at all, that transistor is off.
Right.
Looks like an open circuit, so we're going to have 5 volts here. Once we apply a positive voltage to the base here, transistor is going to conduct, it's going to look like a short, very high conductor, and it's going to bring this voltage down. So most of your gates are inverting anyway, so logically it's simpler to have a positive gate, but because of the very nature of a transistor, inverts it, most of the time we use inverting gates. Okay. So in this case here, if we take the outputs from both these collectors and combine them, either one of these going high is going to bring this low, right?
Okay.
If that goes high, this transistor turns on, brings that low. It's either both tied together, turn that on. So that's your OR gate, or NOR gate, you say. NOR gate.
Wouldn't a negative OR be an EOR?
That's it.
Oh, yes.
These guys. I have a dad, I'm allowed to tell that.
Yeah.
There you go. And I know about 20 kids that work for me too, so.
Okay, and here's a NAND gate.
Huh,
Okay,
okay, wait,
these
okay.
both have to be turned on for getting current through here. These two transistors are in series, right?
Okay.
So turn this one on here by itself, that one's still open, and
Okay.
that's gonna happen. If that's on by itself, nothing's gonna happen.
Ah,
Okay, I thought a transistor,
Here's our output here, and here's our 5 volts.
right? This wouldn't have to go to this side to do that though, right?
No, the current,
It's,
the current that we're looking for is from the emitter to collector.
oh, okay.
right,
So
and then if that's
Okay.
closed, so they both have to be
I was,
closed in order for it to flow. Okay.
I like that.
I had a 96 baud rate fax modem sound for my ringtone for years.
Really?
What I loved was the blue screen of death Linux screensaver.
Oh,
Oh, wow. Oh, yeah.
Anyway, that's the
So you're, okay, you're saying that those would both have to be on,
for this to go out.
right?
and that's what's in a
Man,
chip.
yeah,
A little tiny chip could have thousands and thousands of those
a whole pile of
transistors.
That's an AND gate. Yeah.
But if you look at a chip under a microscope, you're going to see thousands and thousands of those inside of it for like a memory chip. Is that how I'm understanding this?
Yeah, here's some multiple. These are like quad NAND gates, so each of those actually has 4 quads in it.
Man, you see these all the time in electronics.
Yeah.
And this does what?
Well,
It's a quad.
So are
one-
those lined
got
up?
4 NAND gates. Or those, I'm not sure the exact numbers of those.
Sure.
Yeah.
Huh.
4 NAND gates, 4 gates, or all sorts of.
So this is basically like squeezing
Probably
a
about,
whole bunch of
probably about 50
transistors,
transistors.
50 transistors into one little
Because it's
to build a logic
two
circuit.
transistors.
Well, I should do a schematic of a 741 op amp. Those op amps are playing with all the time.
Yeah,
They have about
you do get one like,
13 transistors in them. I think.
wow. Huh. Two.
We haven't talked anything about power supplies, have we? Rectifiers or anything like that? No, I guess we haven't. Okay.
I thought you mentioned a power supply for like 12 volts.
Yeah, but we just said it's a battery.
You just
We
said, yeah,
Okay,
okay, so yeah.
Okay, let's talk about power supplies.
Like an AC to DC power
Yeah.
supply? Okay.
So, here's a typical power transformer here. So, how do we get nice, smooth DC out of
AC?
AC?
With a full bridge rectifier.
That's one of several ways. So let's take, start with the crudest first. So first we would need a transformer, most times. We got 110 volts coming in. 120 nowadays. So it's all we are, we're off of 110 and 117 and then up to 120 finally.
Robots in disguise.
Yep.
So, let's say there's a 6 volts and what we have. This is, let's say 6 volts RMS. Okay, so what's the peak-to-peak voltage of 6 volts RMS?
Tell me what RMS means again.
Root mean square.
Means-
That's your normal way of coming out of the wall sign. That's 120 volts RMS.
Oh, yeah.
And then once you've run it through a transformer, it's down to 6 volts RMS.
Right. But what's the peak-to-peak voltage there?
12? 6 above?
No, it was a weird equation, because
Oh, it's,
120 volts was, like 300,
No.
I don't remember.
What's the ratio of peak to, what's the ratio of peak to RMS?
I'd have to get my notes out.
And that is the square root of 2.414.
oh,
Okay,
square root
and
of
a
2.
peak to peak is twice that, so it's 2.8. Times that, so that's gonna be your peak to peak voltage here, right?
6 times 2.
6 times 2.828.
Might be able to do that.
Right. Okay.
Richard.
Why was it the square root of 2 again?
Because that's the magic number that appears all through the universe.
Okay.
16,968 is what I got.
Mm-hmm.
So that's 16, almost 17 volts
Okay.
RMS. Or, no, it's 6 volts RMS. The peak to peak would be, we'll say 17 volts.
Okay, so what's just the peak? What's half of that? Just to the peak voltage?
On top of that?
Yeah.
7.5?
So, okay. So you- peak voltage. Okay, so our point here is to get a nice smooth DC voltage, right? So the simplest way we can do that is we take a
8.5, sorry.
what is it?
8.5.
Oh,
That's your peak voltage,
that's your peak voltage. Okay.
8.5 volts.
8.5 volts. So,
Huh.
let's put a resistor here, because we always have to have a load in anything. Okay? So, what does a diode do?
It only allows current to flow one direction.
Well, it allows current to flow in one direction. Right? So what it does is, once it's conducting, well, there's a very small forward voltage drop in the diode. It's about 0.6 volts for a silicon diode. Let's ignore that for now. Come up with basically what we have. So if we have, looking at this voltage here, we're only going to have the positive peaks coming through there. Right?
If we do what?
We're only going to have the positive voltage coming through there.
Because the
Because the
diode
diode-
will let it come
Right.
backwards.
So if we were to plot that, we'd have something that looks like this.
Oh,
A pulse of 8.5 volts
Right.
every 60 hertz.
8.5 volts.
huh.
Okay. Not a very good signal. We're gonna have to turn audio happy though. We're in something, okay? Now, what we can do is we can, what's a good way to fill in the gaps here?
Capacitance.
Okay, we put a capacitor here that charges up, and it charges up to the peak. And everywhere it charges up to the peak there, we now have, if we look at the envelope here, it will discharge a little bit between cycles here, but we'll have something relatively high there with some ripple in there.
Yeah.
With some time. We have an infinitely large capacitor, we never discharge in between.
Right.
Cycles, but we have our load here and our RC time constant is we're going to determine how fast it discharges between there. So we can figure that out pretty simply. So,
Still dirty though.
okay, it's pretty good. So, what's the next step to rectify our goodness here?
An inductor.
Well, you've got peaks and valleys. Would you have 2 transformers, each working out of phase?
Or a split transfer. Usually the way you do that is you have a center tap transformer, and I believe that's what that is.
Huh.
And you have another.
Oh.
You then have another
Oh,
rectifier there.
right.
And now what you have, actually you would have.
Another
split,
diode?
another diode. Yeah. And this is called a four-way rectifier. And rather than having that, you would have this.
Okay.
A four-way rectifier.
Makes it a shorter distance. from
A
that.
shorter distance in between, so you need less capacitance to fill this.
Right.
Okay.
And why does it have it closer together like that again? Why was that?
Because
100
we aren't
yards
just throwing away the bottom half, we're actually inverting the
Oh, yes.
half, we're flipping it over. and bridge rectifier is like this. This.
Huh.
This. And apply the power with transfer across the horizontal parts. And output between there and there. And that will
Really?
also be a full wave rectification.
Oh, we do the same thing, just like that.
Same thing.
Right.
And,
Right. Right.
Yeah.
And then you still need a capacitor in there. So is that clean enough? Is that much cleaner? Is that?
I still want to put a filter in there, basket in there. Let's see.
Okay. Oh.
Prefabricated ridge rectifiers. Monolithic ridge circuits. I don't have to put 4 diodes together. Diodes.
Boo. Really?
Well, that's a rectifier too.
Yep.
So you got AC in the middle,
AC in the middle.
and then positive, negative.
Huh.
So if you put 120 volts AC into the middle here, it would, whatever it's designed to output, let's say it's
Yeah.
6 volts, just
Yeah.
to stay with your example. How clean would that, what would that look like?
Look like that.
So it wouldn't be a straight line. It's
No.
not a true
No,
DC.
you'd have to put a capacitor across here to fill it.
Pretty cool.
Okay.
Okay.
Now, in all cases, this voltage here, once you filter it out, is going to be your peak voltage.
Peak.
Yes.
Right.
Now, what if you don't want the peak voltage?
What if you don't want the peak voltage?
What if you want it to be the RMS voltage?
Then, hang on.
Resistors? No.
If you just want the, oh, for crying out loud. You would have to,
You want to lower the.
no, that would still be AC.
Right. Resistors wouldn't do it, would they? No, that doesn't change that.
If you only wanted the 6, so if you wanted a 6 volt DC,
Load?
If you want a 6 volt DC rectified filter, that's included.
is that an inductor?
Or choke input filter.
Really?
So a choke input filter gives you the RMS voltage output. and
Choke input filter.
Yes.
Because
Because what it does is the choke
increase the.
will always want to go to the average voltage that you have there.
Okay.
So it's going to want to average out where the peaks are. So put a choke in there, and you want to choke. There's a minimum value of chokage that you need.
Okay.
But a well-designed choke input filter will give you the voltage outputs.
So if that was in, if this was, go back to your plumbing analogy, a choke filter would be basically just a large section of pipe to
Yeah, it
absorb
would be a
the,
storage pipe. Yeah.
with like say a bellows on one side.
Yeah.
So it would take the peaks
Yeah.
and level them out
Level them out.
by using inductance on an electrical circuit.
And so choke input filters are used in most of your transmitters, high power transmitters, because they're not because you don't want the high voltage, but they're smoother and they're better regulated. So you load this capacitor down, the more load you put on, the more this discharges between cycles.
Oh, yeah.
The choke input filter has much.
So if it's a 20 amp, if it's rated at 20 amps, then you get right up to that 20 amps. You're using every bit of that.
Yeah, so
capacity.
this will actually have less voltage to start with, but it'll stay steadier.
Huh.
So, And then there's another type of choke, it's called a swinging choke, which is even better. What happens is, the more current you draw, the inductance reduces, so it'll actually compensate for the drop you have in there. So I really like the interesting whole thing. So
Is that because of heat or something? That it,
no, not because of heat. What happens is you're actually saturating the magnetic core. Whenever you saturate a core, it loses inductance, so the inductance drops down, so you now have less resistance with higher current. So then,
wow.
You can't hold any more magnet.
yeah.
So if you open up a power supply, what would we see on a modern power supply? Which a regulated power supply would look more like that with a rectifier.
Why don't we do that? Oh yeah, we got plenty of time.
Let's take something apart. You love that stuff, don't you?
Yeah, that's how you really learn. Probably the math.
Sometimes you learn you shouldn't have taken something apart.
Right.
Decided,
And you just gotta hide the extra pieces.
Yeah.
Here we go, you may have the honors.
Oh, wow.
Cross tip. Are you sure?
Anything we break here, we can fix.
You could book it. Don't lose it.
You know what MFJ stands for, right?
Mighty fine junk.
MFJ makes so much
Do you
hamburger.
want me to come around or just?
Oh, you can, sure, if you want to. Or you can just take a close shot from that side if you want.
Okay.
Leave it to the artistic choices of our cinematographer.
It's just tricky trying to get around there.
See what you get when you ask questions.
You get a screwdriver handed to you.
Yeah. So.
That's just, what it's gonna do is gonna average everything out to
To a lower voltage.
It's gonna actually give you a lower voltage.
This is going to have the higher voltage. But this is a lower voltage, but steadier. All right. Taking the cover off of anything, you always got to watch for capacitors that are still capacitating.
Not that, so, probably not as bad as it was for a year, but
You gotta plug it in.
So here's your transformer.
Yep.
Here's your transformer.
You want it on? No.
Oh, no, okay, I thought it was this thing going on.
So here's your transformer. And you've got
Okay.
switch. These are your big wires.
here's rectifiers there.
Rectifiers.
Really?
I don't see an inductor yet.
That does not have a, that's
This
a
does not-
capacitor input filter.
Okay. So this uses capacitors, which I believe.
No, those are, here's your capacitors down here.
Oh, they're over here.
Yeah.
So there's the
Oh,
capacitor
really?
bank right down there.
Yeah. Okay, so you said this is your transformer,
Rectifiers and the
rectifiers.
capacitors.
Okay.
Whenever you take anything apart, it's a water flop, you can sweep the dust.
This was heavy.
Yeah.
Yes. It never gets cleaned unless it dies, so.
And the fan cools the rectifiers?
Fan cools everything.
Why? Okay.
Yes, it's got heat sinks on the, let's see, what's the main thing that's got? Yeah, it's rectifiers and the pass transistors. So we'll talk about regulation.
So what were the white ones on top are
Those are,
resistors?
yeah, those are emitter resistors for the pass transistors. So we'll talk about the regulation.
Okay.
So far we haven't talked about regulation. We're talking, other than brute force regulation, we just make the components so large that you don't have a problem. Most of your modern supplies here, you have to use some of what's called active regulation. So we start with a device called a Zener diode. Zener diode.
Zener. I gotta take like a minute and 30-second break.
Okay. See my blackboard off. Great thoughts and previous knowledge accumulated.
Right. You go Sam right there.
Has a smidgen of accumulated life in here.
Can you use pressurized air to clean that? Or
I sometimes do. So.
On the shelf back there by the bathroom next to your bins full of tubes, are
Yes.
those regulated power supplies up there?
Yes.
There's 4 of them?
Well, there's about 30 of them.
Oh my goodness. Those are 12-volt regulated power supplies.
Well, they aren't all 12 volts. There's some 40 volts. Yeah, those are all
Wow.
Lambda power supplies, really top end stuff. So, probably have 1,000 pounds worth of iron.
That's some pretty skook up stuff up there.
Yeah. So they're all gonna eventually go on my website to sale. So,
All right.
which Jill has been so magnificent as.
Oh, we've got to get back to that.
Yeah, we do.
Because you can use those for power radios.
Oh, absolutely.
Those are clean, aren't they?
They are. All analog switching regulators and old school brute force stuff.
Yeah. Seems like an awful lot to go through just to have a cigarette lighter on the front.
I know. Very well filtered cigarette.
Yeah. Want me to put this back together for you, or do you want to leave it?
Oh, I'll leave it open.
Okay. And then these are heat sinks over here too.
Yeah, these
This
are
is
your
all-
pass transistors here.
Pass transistors.
Yeah, we'll get right into those. Next semester, Jill's going to teach a class, right? Next semester, you're going to teach this class.
It won't be in this subject.
It won't be this subject, as I said.
Okay, so this here is a Zener diode. And if you know it, how do you know it's a Zener diode? turn your head sideways, and this thing looks kind of like a Z.
What if it was a W?
That is really cool. Okay.
A wiener diode.
I knew it would.
Now, remember we talked about the characteristic of a normal diode. There's a forward voltage drop for silicon is like 0.6 volts. And we increase forward voltage, we have this thing kind of looks like this. Okay. The Zener diode has a very well-defined negative voltage drop, which is very sharply defined here. Okay. Now you can get a little bit of regulation off of the forward drop, but on the negative drop. Now on a normal diode, if you run it to where you start getting this, the diode will burn up. You don't want to run the diode enough negative voltage where you start getting negative. Zener specifically designed to do that. Now, since this knee right here is very sharp, it's got a very well-defined voltage drop. So what that means is if we have a resistor here, and we give a supply of some voltage here, and let's 12 volts. And this is a 6 volt Zener. And yet there's no way you can look at a Zener and see by the stripe or anything. So the anode or the stripe end is going to be on the opposite side for Zener. So you put these in the circuit backwards compared to a regular diode. So your stripe is going to be on the Z side, and your high voltage is going to be anode is going to be down here. So what happens is, as long as this voltage is greater than this voltage coming out up here will always be at 6 volts. Often, always have 6 volt drop between here and here. That means anything you put parallel with that, any device you want to drive is also going to have 6 volts across it. Okay. Now, there's a couple of caveats in here. This resistor has to be small enough so that the voltage division between that and that doesn't all drop it below 6 volts by itself. Okay. So you have to have these values of resistor, and this could be your low variable resistor, which is a variable resistance. And this dropping resistor has to be a smaller value than that. But what happens is when you do that, you start dissipating a lot of resistance, a lot of power in this resistor here. Okay? And you start dissipating power in there. Okay? So there's a limit to how much regulation you get and how much power you can drive. This is called a shunt regulator because your resistor or your Zener diode is in shunt with that. So how do we amplify the effect of this to make this capable of handling a lot more current than the Zener diode or the dropping resistor can handle?
Line them up.
Line them up. Well, what we do is we build the same voltage sensor, voltage reference now, and we'll call this our voltage reference. And we use that for the base, what's called a pass transistor. And this will go to the power supply, so this is plus 12. And this is a 6 volt here. So most of your current's going to go into the transistor. And this is what's called an emitter follower configuration, which doesn't give you any voltage gain, but gets you a huge amount of current gain. So the current passing through the base here is a very small percentage of what we have powering whatever our load is. So our load is going to be up here. And so this pass transistor does most of the work. All the Zener does is give you a reference voltage for the pass transistor. Now, in any transistor that's 0.6 volt drop is also going to appear between the emitter and the base. So this output is going to be a little bit lower than the Zener voltage. So that's why your Zener's coming oddball voltage like 6.2 or 6.8 volts to compensate for that. Drop. It's going to be a drop on it. But it's going to be fully regulated. So this thing can handle a huge variation in your load and keep the voltage regulated. Now, normally,
okay.
So,
Current. Okay, so it's regulating the voltage perfectly, and it allows for huge current swings.
right. Now, typically, for example, this is a 13.8 volt output. You run your normal voltage up here about twice your output voltage. So you're actually dropping quite a bit across your output resistors. Now, this is only a very simplified circuit. What we can do here is rather than going directly to a load with this, we can use that to power a bunch of other transistors, which is in this case. So that output there in turn goes to a series of parallel.
You were close to stacking them up.
Yeah.
Line them up.
Yeah. You don't stack. Yeah, you don't stack up the zeters. You stack up the fast transistors. So
In parallel?
these are all parallel.
Okay.
So now you've got,
But then are you adding the volts?
No, the voltage stays the same.
it's all 6
But
volts.
the current capacity is greatly increased. And here's your past transistors here.
3 of them.
3 of them there.
And they're cemented to that heat sink, so they must
Yeah.
dissipate
So
some
yeah,
heat
so
too.
this heat sink dissipates a lot of power. I don't think
So where
there's
does
any
the,
So that's how you're adding like watts or volt?
that's,
more. Well, this thing will handle at 24 volts or 12 volts, it will put out 30 amps. Fully regulated. So that means that voltage will stay absolutely rock solid regardless of how much current.
where do the volts go? Is it converted to heat?
It's converted to heat. That's why these.
Is that why
things have
that's such a huge heat sink in a
Yeah.
fan? Because you're
Oh.
basically taking that and just burning it off
Yeah.
to lower the
Basically, these past transistors look like they're in series with your load. But there's a changing value, so as your load changes, these change to compensate for it.
Huh.
So it's actually a voltage divider between these and your load.
Mm-hmm.
Okay.
Fancy. But inefficient.
Well, it's clean.
It's clean though.
Clean.
You have exactly 6 volts
Yeah.
all the time.
And you
Whether
don't have
it's 1 amp or
any
20
RF
amps.
noise generated like you do with switching.
Right, switching regulators are terrible for radio.
Now, a couple of revisions on here. This has actually has a variable voltage on here within a certain range here. And so, remember our comparators? What we use the comparator for? We have a reference voltage here. So rather than running this thing directly into here, we can take an amplifier, take a sample of a reference voltage here, from here. Our output is used to drive here. And then what we have going into here is actually a sample of our output voltage. So if our output voltage tends to want to change, this will compensate for it. So we have a complete feedback loop there. And then what we can do here, how do we change the gain of an op amp? Well, something like that. Okay?
Variable resistor.
Okay.
Okay, so that's our feedback resistor, and that's how we do adjust the voltage on that. So it's adjustable but fully regulated. So 723 op amp is right down here.
That's the op amp?
Yeah, and that's a very, very commonly used op amp for voltage regulators.
It's gotta be pretty big.
That's not.
No, op amp's not doing anything.
Wow.
All the
No?
op amp doing is just taking for the reference and feeding that back to this driver transistor.
Oh, it's just taking your rep of your output.
Yeah, so take a
Feeding it
sample
back.
and giving the voltage, which is inversely proportional to the output.
And what does that do? It tells
That tells us, so it allows us to adjust this voltage here.
yeah.
Plus, it gives you a positive feed or negative feedback, so any voltage drop we do have across here is compensated for.
Instantly, it's gonna add.
So, for example, if you have long power lines, you got power leads, and you got a voltage drop across them because of resistance,
Right.
That'll compensate for it. You can put a sample at the far end, and it'll come back here. In fact, all those lambda supplies have actually 4 terminals for the output. They have the sense line, which takes the output from where, so you can put really long lines with a lot of power loss there. You sample it at the far end,
Right.
Wow.
and then so if that voltage drops, it increases the voltage.
So if you want 13.6 volts at that, and it might be 14.2
Yeah.
over here.
Yeah. It'll compensate.
And that would adjust automatically if you had loads increasing or decreasing, transmitting and receiving.
Yeah, like I say, the negative feedback covers a multitude of sins.
Feedback. And where, yeah.
This has a few other features to it as crowbar circuitry, so for over voltage protection, if something should go wrong with your regulator, so you don't torch the device downstream, and it's called an SCR, which fires and it puts a dead short on it, so that it blows the fuse here rather than frying.
Sure.
So that's your high current power supply, to have some sort of crowbar circuit.
$200 power supply on a $4,000 radio.
Yeah. So that's
That'll just shut it out.
yeah, this, I'm trying to think of something there. I know it does have it in here. Oh, yeah, you were asking about the resistors here. Those are equalizing resistors for each of these here. Because a transistor tends to go in, as they get hot, can go in the thermal runaway.
Oh, yeah.
And so you equalize the current on each of these transistors so one of them hog all the power. That's what these resistors are.
So that they're all working equally
Totally, yeah.
versus one hogging it. Okay.
Okay, so
Zener.
that's
Wow.
that's your regulated linear power supply.
Variable even. I love it.
Since so much of the stuff has switching regulators, including all your computers, by the way, do a passing mention of them. In anytime we have a series element dropping power, we dissipate power. That's why this thing's got huge heat sinks on here. So
Right.
the normal load there, you're going to dissipate power. And how do we get a real efficient power supply in a computer and still be fully regulated? Well, what we usually use is a switching regulator. So there's some more sophistication to this, but basically what we start is with an oscillator. And it's usually like 40 kilohertz or so. And that can depend on a lot of other variables that you have here. We go into a high frequency transformer. And by going to a higher frequency, you use much smaller transformers. That's why aircraft uses 400 hertz to go to 40,000 hertz, you need much smaller.
Huh.
Now, rather than using a dropping resistor to regulate the voltage, what we do is we rectify this into a very high voltage, much higher than we want. And a couple ways we can do that. We can use a conventional rectifier, or use what's called a flyback transfer. So we have a much higher voltage, we want very high frequency. Okay. Now, since it's such a high frequency, there's such a small gap between each of the pulses that we have here, we can use very small capacitors to filter that out. So now we have a very high efficient DC voltage. And now what we do is we take another oscillator, or we can use the same oscillator, and we use that oscillator to drive a fast transistor, or several of them. And what we have now is we have a square wave, which we changed the duty cycle. Now, we can make it a very wide duty cycle, or narrow duty cycle. I mean, that's good. Narrow duty cycle.
Oh.
Now, if this is switched perfectly on or off, the only time you dissipate any power is during the actual transitions. If If it's fully on, you don't dissipate it. If the switch is closed, it doesn't use any power, right? So we absorb resistance to the switch. If the switch is open, you don't have any power loss because you got an open circuit, okay? So what you want to do is you want to make the transitions between a fully closed circuit and a fully open circuit as fast as you can. So we use these very fast switches, SCRs is one of them, silicon controlled rectifier, and sometimes just very fast FETs, which are used to switch this at a variable duty cycle. So what we do to regulate it, we have another comparator, okay? And if we take aside this wave here for a secondary wave here, and we make a ramp here. Remember a nice little sawtooth ramp generator or function generator? We take this signal and we put it into a comparator. Okay? What's a comparator?
Gonna measure the peak voltage with the,
It's going to compare two voltages.
two voltages, yeah.
So if we put a square wave into this side here, and we have a comparator on this side, we put a ramp in here, what we have here in this particular case, this square wave is going to, when this is very low, it's going to maybe have a low duty cycle, and as this increases there, it's going to turn on faster, so now our duty cycle is going to increase as we're farther up on this ramp. Okay? So if we have a separate second oscillator here running this ramp here, we can determine the duty cycle depending on where we turn this ramp on.
I'm assuming it's the same frequency.
Same frequency.
Same
Yeah.
frequency,
Yeah.
okay.
So we turn the same, everything here is on the same frequency here. But what we can do here, by changing the duty cycle, all we have to do is put a small DC bias on this ramp, so we can shift the ramp up and down a little bit. So the difference we have to actually go through another. We just add a DC voltage to that. So that we have this ramp, so that as we increase the voltage on the ramp here, this turns on a little faster, or move the DC ramp down a little slower. And what do we do to change this voltage here?
A feedback from
Feedback loop from there goes to an op amp or two, this can be pretty sophisticated.
Wow. And what you're trying to do is fill these in?
What you're trying to do is keeping this duty cycle enough to keep the voltage, because the voltage is going to be proportional to the duty cycle. So this is going to be rectified again after.
Oh, okay.
Yeah, this goes to another integrator. So this goes to an integrator, which is usually a choke filter. So it's a choke input, choke filter. We talk about choke input filters. Goes to that, and then we get the DC voltage, which is proportional to the duty cycle.
And this is what most computers
Most
use?
computers do.
Because of
It's
the
very
high,
efficient, extremely efficient, because
it's
you
small.
can either on or, because it's on or off the high frequencies, give you small transformers.
Yeah.
The fact that it's switching is either on or off. That's the only place you use any power output.
Yeah.
And we don't have any series resistance, so it's the only time this the faster you make that transition from 0 to 1,
Yeah.
the less power is going to be dissipated. So you do want to have very fast switching transistors in all through here.
But no matter how fast it is, you've still got 0 volts and positive volts
Well,
at a very high
0
frequency.
and 1, yeah.
At a very high frequency.
Yeah.
So you said frequency so many times, I'm guessing that this wouldn't be a very good thing to power a radio.
Sure would.
It would?
Yeah. Most of your
Switching.
Yeah, switching rate. Yeah. But the efficiency is so high because you aren't rather than having a resistor element, and that's what these passive transistors really are. They're just series resistors. What you're doing here is you've got a choke there, so you're just turning.
That's where you get you lose your values when it goes through the choke.
Yeah.
Then it becomes a more
Yeah.
steady. Okay. So a switching power supply wouldn't make as much heat then.
No, the only time you're making heat is during the transitions, which are very,
Very
very short.
short.
Very short.
So less heat, less waste, and still clean power.
Well, mechanically. Cheap power,
Right, so
You make it clean at the end with the inductor.
Well, yeah, and, but there's other filtering, so you've got all these oscillators going here upstream there, and they can create all sorts of hash and stuff,
So the old power supplies that had tubes in them, that would be your transistor, would be the
Well,
tube?
actually, let's go back how we got high voltage supplies and.
What do you lose in this, though? You lose something because you're not generating so much. Do you lose like a lot of information, or you lose
What the main disadvantage of them is they do generate noise.
noise?
Where there's no process of noise in a DC circuit. So you have several places here which can generate a lot of hash if there's not a lot of careful design, but you have to be better shielded and that sort of thing.
So I would imagine, like, let's say heat wasn't an issue because you were just blasting in Arctic air into,
Well,
then you could create something that had less noise. And, well, we don't have to get into it, but I think there's an advantage there, right?
well, I mean, if you put this thing out at 60 below, it's probably going to run a little more efficient. Let's talk about old-fashioned, like how did you get plate voltage for a car radio back in
Yeah.
40s, okay?
Okay,
And think about a vibrator, okay? A transformer doesn't work through DC.
DC.
So you have your DC in with your car, went to this vibrator, which was basically a buzzer, okay? Got electromagnet, which now pulled in a set of contacts. And then the set of contacts was in series with that, so when the contacts closed, it opened its own circuit, or you had a secondary pair. And there were both synchronous and asynchronous vibrators. So you simply had this circuit which was just a buzzer which would vibrate and make it break the circuit on a transformer.
Okay.
And that would be fed into the primary of the step-up transformer.
How quickly do you think that was happening?
Well, we had a couple of 100 hertz there.
Right, because that's a physical.
Yeah, it's a physical vibrator.
Oh, okay, yeah,
It's
okay.
just a vibrator, just a
Yeah.
buzzer.
Yeah, okay.
And you used to have to replace them along with their tubes. They had little cylindrical things with 4 pins on them, and they had a little buzzer
Right.
inside. They usually have some padding and some, shock absorber. And that would go to your high voltage, and then this would go through another rectifier to rectify your high voltage for your plate supply, where the tubes would need high voltage. Now, synchronous rectifier would have another set of contacts on here, which would do the function of the diode. It would swap the polarity on these. So you had a buzzer in there, and it would swap the polarity because the buzzer would have a set of contacts here. And so coming out here, it switched to one side of the transformer. We have a transformer here. And there's a 12 volt.
So the only time it was off was when it was between the two wires,
Yeah.
otherwise it was.
Yeah, so it'd sit there and oscillate and swap the polarity of the transformer there. So it's a mechanical rectifier.
Yeah.
Which, how many have been around diesel trains close to the locomotives in the early days? I remember we grew up near the railroad station. I remember hearing this really gnarly rattle of diesel trains. Because all diesel trains are diesel electric.
Yep.
They always have.
Oh.
They've got DC motors. Well, back in the 50s, they didn't have rectifiers good enough to run tens of thousands of watts. They had mechanical rectifiers.
Wow.
They had these vibrators, huge things. And when
Really?
they were like a hair trimmer, and first it would be like that, except 100,000 times. And we were always hearing that in your railroad because you're the tracks there.
I remember living near a tractor station. I remember that.
I very, very definitely remember the sound of those beats.
You probably followed the no trespassing signs, where you did.
No, right. We didn't have to trespass.
Why did they need to be so big?
Well, you look at diesel engine, 3,000 horsepower,
It's a lot of amps.
to be able to handle a current,
Oh, okay.
be able to have a current for the motors, traction motors.
Okay.
Yeah, typical diesel engine, diesel locomotive, 3,000 horsepower.
Quite a bit.
But the reason they do that, you can keep the engine running at the same speed, and then you only run the regulation for the motors, which is very efficient. Diesel can be very efficient as long as you're accelerating.
Running at it, right.
Diesel at the same speed. Mechanical rectifiers.
Mechanical rectifier.
I mean, I'm sure they had to change those out all the time.
Oh, I'm sure they did.
Yeah.
Then they went to,
It's a lot of movement.
then they went to, ignitrons, which is the mercury, like an SCR.
Huh.
Your earlier welders, DC welders use ignitrons, which is basically a container of mercury with a high voltage conductor on it, then you had an electrode which would fire the thing. And once they fire, they stay fired until you reverse the polarity on them. So, an SCR, well, let's see. Let's talk about firetrons. You'll never see a firetron as long as you live again. The firetron is a gas filled tube. The little dot here means it's full of gas. And it's got a grid in there. And got a voltage on here. And like any tube, if it's just sitting there, it's off. Once you gave enough voltage here for this tube to fire, you get ionization across the gas in there, it would stay going, okay? The only way to turn that off is to reverse polarity here. So it is and that has exactly the same characteristics as a modern day SCR. Your SCR, silicon controlled rectifier, which is used in all sorts of power supplies, is actually an NP-NP junction transistor. And once you turn this on, it stays turned on until you kill the voltage on your output here. So they're used for all sorts of high power switching and regulators.
So you have to create it open?
You have to create,
You have to create it open on
circuit, yes.
Okay.
What's called commutating it. SCR someplace around here. These.
Makes you look at every single electronic device a little differently.
Doesn't it? Just a thought.
I mean, every little thing you've got around you has got.
No, I don't have any big SCRs right now.
History.
I got some living ones.
Knowledge that it's big enough.
But yeah, it's a trigger circuit, so once it fires, it stays fired until
Wow.
it. So. But the advantage of that is because when it happens, it's very fast. It's got positive feedback, so a small trigger, you got the transition time you're talking about is extremely small on an SCR. Yeah, also back-to-back SCRs, which are basically full wave SCRs, and those are called triacs. So if you're here, the term triac is basically two SCRs back-to-back.
Okay. Full wave.
Full wave, yeah.
Because there's two of them. One
There's two of them, yeah, one for the positive side, one for the negative side.
Wow.
Yeah, there's a whole different world of power transmission stuff. For example, in China, they use a lot of DC power lines, Well, how do you get it down to, running 3 million volts of DC here, but how do you get it down to usable voltage here? Well, you don't use a resistor there, you have to re-convert it into AC, then run it through a step-down transformer. And so the only way you can invert that is have monstrous SCRs that are capable of doing that, So the Chinese are actually far ahead of us in DC technology for that kind of high power stuff. So.
Really?
Of course, we aren't pumping electricity across 3,000 miles of Gobi Desert either.
Right.
So,
Okay. That's their benefit is they get to have so many volts and that really pushes it.
across nothing.
That's why they went DC hot.
Well, DC, a couple of advantages of DC. You don't radiate anything with DC. The problem is with the 60 hertz, it's at some length it starts becoming an antenna.
Right.
Whereas DC will never do that. Plus, your insulators only have to be insulated for the RMS voltage, not the peak-to-peak voltage. When you got AC, your insulators have to handle the peak-to-peak voltage.
Right.
So your insulators are already down to about a third of the before they get amount of power.
Wow. Yeah.
The amount of voltage.
Voltage or what?
Voltage, yeah.
Voltage.
The insulator has a voltage breakdown. So. Now, here's the question. Why do they go up to high tension lines? Why do the insulators have little corrugated wrinkles on them?
Why do they have the insulators?
Yeah.
In case they get wet, I would say, or Oh, okay, I wasn't sure what you,
That's the wire, that's what the wire?
no,
is?
that's the insulator.
Yeah, the insulator stuff.
So they're ceramic,
They're ceramic, yeah.
and they got like,
It's on the
stacked,
inside
they
of
look
the wire?
like stacked discs.
But that,
I haven't seen one, is that on the
well, if
inside
you
of the
go
wire?
to the high tension wires, out the Channel Valley Flats, any of the real high tension,
Yeah,
high power wires, and look what the wires are suspended on.
oh, yes, right. Why is it on
Yeah.
that?
Why is it
What is that?
wrinkly like that?
Extra surface area for heat dissipation.
It's the length of the leakage path.
Okay,
If they were straight, it would only be that long. They make a long path there. Any leakage for the electricity has to travel a long distance to get from here to here.
Because it's not the distance
Have we
through
talked about
space, it's the
leakage?
distance on the,
Yeah. Well, we assume that there's always going to be some. There's no such thing as perfect insulator.
okay,
So there's always going to be some leakage. Or, well, if you make the path as long as possible, you're not going to, resistance is going to be very high.
oh, and leakage of what?
Electric current.
going to ground.
Of current,
Yeah.
Yeah, it would go to ground, that's where it wants to go.
uh-huh. And what are those made out of?
Ceramic,
They are,
porcelain.
so they're also insulated,
They are, yeah.
and, okay, I see.
But they're not a perfect insulator.
Right.
And if you have any moisture in the air or whatever, you know.
They have to wash them in Florida, because they get salt water on them and they start to conduct. So they wash them with distilled water,
Still water.
if they don't get rain enough.
Beaches?
Yeah.
They really have to go do that?
In
Well,
Florida,
they lived in
Or anywhere
beach
with
cities
salt.
there, they were always doing that because, the salt
Right.
air from the ocean.
Oh, wow.
it conducts electricity.
You start hearing the hiss on them, and they're
Yeah.
dying for that.
So the potential between peak to peak is why you measure voltage, because of the difference in potential
Yeah, your potential is going to be.
on an AC current like
Yeah,
that.
AC
So,
is going to be your peak voltage.
wow, okay, something just clicked with, I didn't quite understand what the difference
Yeah.
was until I started thinking about how far the swing is
Yeah.
from, yeah, okay,
Mm-hmm.
that's your potential
Yeah.
voltage, moving that much.
Yeah.
Okay. That makes a little more sense now.
And then if you got three-phase power, you got,
You go.
you got a whole lot more.
Yep.
Of course, you gain a lot more just by.
I gotta talk to you about three-phase power when we get a chance.
If you're talking about power, you can make a brief sojourn in three-phase.
Sure, I'd like to understand that too.
Well, I have a solid state phase inverter and I have a rotary phase inverter.
Okay.
My plan was to replace the rotary phase inverter with a solid state. And one electrician told me this is what you need, so I bought two of them, one for down in Wasilla and one for here. The electrician that went to wire it up says, no, that's not gonna work. That's just for starting a motor, that's not for running a motor. So I don't know, when you open it up, it's just a whole bank of capacitors in a box.
Yeah, well, I'm not sure exactly for the.
But anyway, a phase inverter, a rotary, you're taking one of the two legs that are supposed to your building and creating that third leg out of phase with the other two.
Yeah. And the voltages are not the same on them. When you do that Texas two-step, it's not.
Yeah, it's never a good
Yeah.
thing.
Well, it works, but it's the math is really weird. But,
The sad thing is I got three-phase power on the lines right out in front of my building
well, I can't use that.
because the pot growers across the street took all the electricity from the circuit.
Well, there's a quick solution.
Really?
There's a warehouse across the street, and
took
when
all
they
the-
started growing pot, there was nothing left for us.
Now, all of you, whether you use it or not, are using three-phase power at one time or not. What's the most common application of three-phase power?
Electric motor.
Well, even more than that.
Oh,
Even if you
sorry.
are doing it for just about every human being,
What's a
with three-phase application.
what three-phase application?
Mm-hmm.
Your brain.
Your alternator in your car.
Oh, is it?
Yeah.
That's three-phase?
Yeah.
Your alternator.
Okay, did not know
Really?
that.
So three-phase power was another thing that Thomas Edison did not
He
understand.
did not invent it. No, right, no, he didn't. Nor did he appreciate it.
It was actually the guy who really developed it, a guy named Charles Steinmetz. And they hadn't met Charles Steinmetz once.
Really?
Very, very old. But they were really good. Generous Electric, Schenectady, New York, which is now disconnected. So, three-phase power. What we have is three conductors, and at any period of time between any of the three conductors, we talk about Eli the Iceman. Rather than 90 degrees or 45 degrees, we have 120 degree phase shift between them. So between this guy here, we have this guy here, and between here and here, the next thing is hard to draw it.
Whoa.
It's actually a little simpler if you draw it in a true triangle. So we have a 120 degree phase angle between each of these two. Now what that does is it greatly simplifies the design of motors, because what we have is we have a rotating field going around there. So all you need to make a three-phase motor is three armatures, and you just need like a squirrel cage, which is just a cylinder with a few wires running through it. And
with 120 degree.
120 degrees there, keep shifting there, and very, very cool design.
And the wires are 120 degrees off as well. I mean, roughly.
Well,
No.
ideally, a three-phase alternator is perfectly symmetrical. Ideally, like if you look at the power lines going across the Tanana Valley there, that's all three-phase, but they aren't in a perfect triangle because it's just as mechanically a little harder to build it like that. Someplace lower 40, you go, well, you have one line in the middle there, and the two there would be the perfect equilateral triangle, which is the ideal way to do it.
That's the way to transfer the,
Because
the magnetic fields are going to
and that'll give you at least less radiation.
Wow. Oh, I see.
So that's a transmission line.
Yeah, the transmission line.
Very cool. And coincidentally, the electric motor is exactly the same as the generator that makes the electricity. So if you think about the steam plant or the hydroelectric spinning the generator, it's three windings.
Is it?
So
Yeah.
when you go to an electric motor with three windings, you're just taking that power and transferring it and spinning exactly the same RPM and everything. 60 hertz.
Yeah, synchronous motor.
We need to take one of these apart.
Yeah.
Wow.
I got some three-phase fans here.
Yeah, it's the most efficient way to transfer electrical energy from the where it's generated to where you're physically moving something with it.
That's why pretty much anything industrial is
Three-phase, because it's the most efficient way. I mean, like Fort Knox, every electric motor on Fort Knox is three-phase.
Yeah.
223 phase fans.
Yeah,
Wow.
for the
And
first.
with that frequency.
Well, frequency still 60 hertz.
I think they figured out the generation portion of it before the motor portion of it, I believe.
Yeah,
Yeah, they were making three-phase electric just because that's how many windings would fit in a generator. And then somebody says, hey,
I don't know where this came from.
And that's how you do it without them going out of phase.
Well,
Because you couldn't have a four-phase because it,
you
have 90 degrees off,
there's
right?
no advantage to four-phase, so it's three-phase. Now, there are what's called interlaced three-phase, which you use in like a lot of high-power transmitters, because when you rectify it, go back to DC, you have interlaced three-phase, actually a six-phase. And so the ripple we have is much higher frequency. So we played around with a lot of that in most of your TV and high-power broadcast transmitters are interlaced three-phase.
You want a brain tickle?
particularly.
So naturally, three-phase power would have three hot wires, right?
Yep.
So naturally, how many would a single-phase system have?
3.
Two.
Yeah.
If you count the ground. Yeah, 2.
Ground.
Three-phase? Well, no, you get two hots.
I know the commercial telegraph license used to have a lot of stuff with
Yep.
phase. I don't know if it's
On
anything
single
with the
phase system,
CR
you've got a black, a red,
But
green,
you
and
should be
white.
aware that there's two
Black?
configurations of three-phase power.
Red, green, and white.
One's called a delta, and one's called a Y.
Yep, black and red are your hots, green, white's your neutral, green's your ground.
And, if you ever worked on any, like fluorescent lights in schools and stuff, where they have a whole bunch in there that run on 277 volts. And where that comes from is, 223 phase, but it's between, rather than between here and here, which would be 220, we would have between here and here, which is 277, or 240. This is called a delta configuration, where you actually have a fourth wire in here, which if everything's working right, you actually don't draw any current there. We have a delta here. And there's all sorts of configurations. You have a transformer, which is a delta to a Y transformer, and that's used on a lot of
So like high-rise buildings,
high-rise buildings,
and all that is like 270 volts.
Yeah, 277,
Why not 240? Let's say that
yeah.
again.
Because 240 between the center, the neutral, and either of these legs, so it would be 240, 240, 240, 240. And whereas you don't need three-phase, you usually just take one leg, or two legs there, so. You'll need 240, just go between here, so you get to supply three different outfits here. But if you need between here and here, it's 277.
It's 277.
A lot of lighting uses 277,
So that's where that comes from.
which I've never understood why they use that so much for lighting systems. I don't know if it's the,
It's usually available, you aren't loading the system down very much. If you already got three-phase, I will use the
that's true, no.
It's more, I was told it was more efficient.
Well, I guess
To
it's
make
more efficient for
electricity.
motors, I don't know if it's.
I don't know about electrical or.
Other than the fact it's higher voltage, higher voltage is always going to be more efficient, so.
Yeah.
And why is higher voltage always going to be more efficient? In any circuit.
Why is higher voltage more efficient?
Yep. Thank you, Julius.
Why is higher voltage more efficient?
Where do inefficiencies come from in electric circuits?
Resistance
Because this is primarily where?
in the wires.
In the wires, okay.
So a higher voltage,
So how do we determine the,
less current,
that's correct.
right? You have less current, higher voltage, so you have less resistance in the wire.
That's where our losses. The higher the voltage and less current, the less loss is going to be, and the more efficient it's going to be.
Which is why the big high tension lines
That's right.
are thousands and thousands.
100,000 volts, yeah.
Uh-huh.
Less transmission line loss.
Also why open wire feed line is lower loss than coax. Impedance is higher, and voltages are higher, but your currents are lower for giving higher power.
It's,
If you look at the back of some of those, like, multi-use bulbs and whatnot, you'll see the difference in amps between 12 volt and 1.
I was thinking of the fluorescent, the higher end fluorescent fixtures. You open up the wires and there's like 240 volts, 120 volts, 277
Well,
volts.
you
You get all the other ones out of the way to get the ones you want.
the balance, sorry, the universal balance of those for everything. I did wire up a 220 system to a 110 ballast and was not happy.
I wouldn't think so. No, I wouldn't think so at all.
Yeah, we replaced all of the lights in Flow Line's office
Yeah.
and warehouse and everything to LED.
Yep.
Because their ballasts were just hogging up so much power.
But even with old school ballast, so it's faster started with higher voltage. Remember the thermal electric starters you used to have on all those fluorescent lights? They went to rapid start, and that was always a lot easier with higher voltage.
I had to look up bonding your neutral to the ground in your panel because I was putting a sub panel in for my Radio Shack, and you don't do that in a sub panel.
Yeah.
You only do it in your main panel. So I had to wait a minute, why wouldn't I? And then it makes sense once you understand how it has to trip breakers. It has to go find its way all the way back.
Yeah.
If you give it another path, you could end up energizing like a box, an electrical box anywhere. Just could be like
Yeah.
240 volts all of a sudden.
Oh, you know how,
Yeah.
you know how GFI breakers work?
Do I know how they work?
Yeah.
Ground fault. No, I'm going to say no.
Okay. Well, this wonderful circuit called comparator keeps showing up.
Yeah.
So what you do is you have,
I know they can be noisy RF noise sources.
you use a toroidal core here, right? And the transformer, both conductors going through the transformer, right? Toroidal. So now, as long as the currents are both equal, what current do we induce across here?
Currents are equal. On an AC voltage, I would say 0.
Very good.
Yeah. Yeah. So they're in phase. So it's like a transmission line. If you have 0 loss, it's going to be perfectly balanced.
Here's an amp, okay?
Just a little one.
This little one. And there's a current. So if you clamp these across both conductors, you get nothing.
Measure 0.
Right? So you have one. So a GFI connector, the reason is because you have equal current going back opposite directions. Okay? A GFI detector detects an imbalance in them. If you have any imbalance in there, then how do you get an imbalance? Because of another path outside their normal conductor. So if you have a path that shouldn't be exist,
Oh, okay.
you now have a path of current through
Somewhere else.
and so the current through there is not going to be balanced. So you are going to induce a current in there, and then you have a
That's what it
comparator
trips.
that fires and says, here it is.
And they trip like on a whim sometimes.
Oh, yes.
Yeah.
That's 0.3 or no,
Yeah.
point.
It trips
It's
below
lower.
the level that you can
No,
feel.
it's
Yeah.
higher now. So it used to be 0.15 milliamps.
Yeah.
I think it's 0.3 milliamps now, because when it was 0.15, you couldn't start your vacuum cleaner without it tripping the GFI.
Yeah.
The initial ramp
Yeah.
up amperage would trip it. But
So it senses it out of balance because
Yeah.
obviously that electricity went somewhere, so we have to shut it off.
Yeah.
Now I know how a GFI circuit
Yep.
works.
So you can work in your barefoot on your 220 stuff there, and then along that GFI.
And I do. My radio room has a box this big and it's all GFI protected.
In the opus of amateur radio knowledge lore, I wrote a little chapter on how to test for safety of electrical, whether you're using 2-prong wires and how to check the polarity on there. And what you do is you take a folding metal chair and put it on the floor, you connect a jumper cable between that and your ground, remove your clothing, and you sit on the chair. And if you feel a tingle, the plug's in the back.
This is it.
there's a guy that has a whole YouTube video about that. Or a YouTube channel.
Oh my goodness.
No. Okay, so we will do an introduction to we're along in the course pretty well. So next week we'll do radar. And we'll go back and cover some stuff. So radar will be some fun stuff. This is a preliminary to radar right there.
Okay.
Yeah.
Ooh.
Oh, that's right, because we're measuring
The
distance.
bounce back.
Yep.
We'll talk about a few of the other cool navigational systems that are out there now.
Yes, that is absolutely a preliminary to radar. Now that you mention it.
You were going to go for the radar endorsement, right?
I'm thinking about it, yeah. Just,
It's worthwhile.
yeah. I'll actually do a full-blown course on that one.
Yeah, especially if you're doing any military stuff at all.
Yeah. I figured out why I was so confused on why I need this cert for my job, though.
What's that?
I finally got the insights today. The whole reason I need this cert is because someone decided to put FAA radios in 3 of our huts out of 97.
Oh my goodness. That's why you
That's
need
why
it.
I've never seen most of this stuff, is because it's only in 3 of our huts. But
It's outside of your world. Most
since
of
we
it.
have the potential to be around it, we have to have the certification.
That's
No
great.
So it's like,
And
but it's cool.
radar
Like,
fun stuff.
yeah, no, I'd be really interested in the radar stuff, because if anything ever happens Mine's are, I could jump over to
Yeah.
Arctech or whoever, you know, like,
I worked for Mertech for a long time.
Oh, yeah.
go
And I'm
hang out
just
in
learning,
the Indian
so I
mountains.
can say I know mine.
They let their guys hunt out there too.
So what you do is you
Yeah.
wrap that around your dog's neck and see if he's got any vibes there. You-
I have a little one of those, or I had. I don't know if I still do
That's
now.
why you have two wires in a single phase system.
It might be
About
buried in a
30
box
feet.
somewhere.
Yeah.
Old Impro.
So each
My air
each
conditioner
wire
issue
going
days.
to each of your outlets, each like your toaster and stuff like that,
Yeah.
has one hot wire. But in your breaker panel, where you put those